Oh, wind. Munchkin. Some cheese it. Cheese. Sour cream and onion. Mmm. Move. Sniper, yeah? No sniper. Shit. Sugar. Why did I pick up a knife? Pick up no knife. That was close, that. Level 9, 199. Hey. Oh, let me get the bloody labels. That's what the labels are sold. Tags. Bare red tags I can see. I'm just out here trying to get the tags. That's it. Oh, got them anyway.
Proximity deployed.
Oh yeah? Okay.
She's gone.
Is that still there? Well, that's still there. Well, they still didn't use it. I'm trying to get that. Fuck off, man. I'm just trying to get that. Oh, look. See? See, I'm about to go and get it, and it's gone. Mm.
Hello everybody and welcome to another Falcon 9 mission from the cave. My name is Iamsarahwildegoofficial, I'm your host for today's Starlink 10-14 mission, which as of right now is targeting to launch in 57 minutes from now. On board there are 28 Starlink V2 mini satellites and the booster per day will be E1077-23. So, let's get this started. As always, if you have any questions about today's mission before I introduce my co-hosts here, make sure to tag at MSF or at Master Space Run in chat. We can also Starship or where you want. Yeah, a bit open for questions today, so let's do that. Alex, how are you doing?
I'm doing fantastic. It seems like it is a very nice day to be watching a Falcon 9. Look at that, sunrise. I was gonna say sunset. My brain's already fried, I guess, from all the Starlink stuff. But yeah, I mean, another Starlink, and let's see how this goes. Look at that. There's a lot of clouds, yeah, but probably not a big of a deal.
Let me ask another person about bad weather here and also introduce him. Hello, Jerry in the field.
Hello, how are you? Yeah, the weather is looking great this morning. There's some clouds low on the horizon, you know, but it's perfect out here. Great morning to be out here at the Cape.
So let's hope that trend continues and we get a Falcon 9 launch in 55 minutes from now. But Alex, I gave it a bit of an intro here, but anything special about this mission that our viewers should know?
You know, there's a funny thing about this, Mister, because
Oh, I forgot Jay. Sorry. I forgot Jay. Oh no. Production will let me know about this.
It's a classic, you know that. So there's a funny thing about this booster because it's B1077 and it is also the 7th booster to fly 23 times. So I find it very, I mean, maybe it's not, maybe it seems, yeah, right? Like 7th, right? 77. I don't know. It's funny with the 7th and whatnot. But yeah, it's you know, just I guess this is the opposite of what Sawyer will say. It is your ordinary Starlink. This is pretty much what you see if you were to go to see a Starlink at the Cape. It's your ordinary Starlink, I guess, for this one. 28 Starlink UTV satellites going into low Earth orbit. Booster, as I said, B1077 on its 23rd flight. I mean, it's true that it is already the 7th booster flying 23 times. Since all the boosters have already done this, but it's quite interesting.
I wish HR had fancy AI agents. You do. We all do. Everyone does. HR, customer service, field service. Finance? Yeah. Engineering, you name it. AI agents are built into the ServiceNow platform we already use. They're literally in every corner of our business. I have AI agents. Well, I gotta tell Jim. Jim's that way. Jim is that way.
It's, well, we basically plants make it for free in Plankton. Yeah. So, it's basically electricity cost of separation and distillation.
Right. Now,
So
remind me though, what is it like, as far as the ratio goes, fuel OF ratio, having a lighter molecule, don't you kind of want that to be spewing out faster or something because it's less reaction and it can be accelerated quicker? Or
yeah, there's a trade-off between, well, I mean, what you tend to get limited by is you don't want to go too close to stoichiometric because the heat's too, you basically melt your engine. Yeah. So that tends to limit you on the on trying to go to higher OF. Right. That's something limiting you. You tend to hit the stoichiometric melting point before you roll over on ISP.
Okay.
Generally.
That makes sense.
Yeah.
And remember, the grid fins, do they still fold in?
No.
No. Is that going to be permanently that way?
Yeah, so what I'm trying to have us all just implement rigorously is the sort of 5-step process. First, make your requirements less dumb. Your requirements are definitely dumb. It does not matter who gave them to you. It's particularly dangerous if a smart person gave you the requirements because you might not question them enough.
Yeah, you might take it as like gospel, like
Yes.
I have to do this thing.
Everyone's wrong, no matter who you are. Everyone's wrong some of the time. So make your requirements less dumb. Then try very hard to delete the particle process. If you're not occasionally adding things back in, you're not deleting enough. The bias tends to be very strongly towards, let's add this particle process step in case we need it. But you can basically make in-case arguments for so many things. And for a rocket that is trying to be the first fully reusable rocket, there's never been a fully reusable rocket. People don't understand. Like, this is like the holy grail of rocketry. Okay.
100%.
And so you really need, you have to run at tight margins, because if you don't run tight margins, you're going to get nothing to orbit.
Right.
So you've got to delete the powder process step, super important, and you can't like hedge your bets. That's why the quick fins, for example, do not fold down, because that's a whole extra mechanism that we don't need.
And you can just compensate for it by having strong enough engine authority to steer it in the lower atmosphere.
Actually, our simulations, so we don't really need any extra engine authority. As long as the quick fins, basically follow the flow, they're not really disturbing the flow. It's really neither here nor there.
So,
as long as they don't have a high angle of attack,
right.
It doesn't matter.
A few degrees or something, or within a degree or two.
So, but in any case, it's a thing we can add later.
Right.
So, now these grid fins are humongous. We'll go see them. But they're like a dinosaur bear trap. Okay, it's like I made a bear trap or a dinosaur. That's what these things look like. And if you have a whole mechanism for folding them, that's like clearly a part that we don't need.
Yeah.
So this was a good design decision. That actually I hadn't come up with, and it was like great, but it followed the principle of like delete the part, delete the process, and I was like, great, good idea, let's not fold them. Why are we folding them anyway? Somewhere random, and also whatever requirement or constraint you have, it must come with a name, not a department, because you can't ask the department, you have to ask a person, and that person who's putting forward the requirement or constraint must agree that they must take responsibility for that requirement. Otherwise, you can have a requirement that basically an intern 2 years ago randomly came up with off the cuff, and they don't even have the company anymore.
Right.
But it came from the, let's say, aeroloads department. They're like, actually, there's no one in the aeroloads department actually currently agrees with that. This is, by the way, happened several times.
So again, it can be literally.
I don't know if you're on the aeroloads department. There's every department.
Right.
So
it can be thought of as gospel again, but it might be something that's just totally in passing. Like,
yeah.
Or someone played too much Kerbal and had fins at the top of the rocket, and then it just, did this.
These things are often just way more silly than you think. Anyway, so step one, make a requirements that's done. Step two, delete the part or process step. If you're not deleting a part or process step at least 10% of the time, basically if you're not adding things back in 10% of the time, you're clearly not deleting enough.
Right.
And then only the third step is simplify or optimize. The third step. The first step. The reason it's the third step is because it's very common, it's possibly the most common error of a smart engineer is to optimize a thing that should not exist.
Right.
Okay. And so how do we why would people do that? Well, everyone's been trained in high school and college that you've got to answer the question, convergent logic.
Yep.
So you can't tell the professor your question is dumb, or you'll get a bad grade. You have to answer the question.
Yep.
So everyone's basically, without knowing it, they got like mental straitjacket on. That is, they'll work on optimizing the thing that should simply not exist.
Right. Right.
I'll give you an example from way back in the day of Falcon 1. So in the original sort of like, when Tom Miller and I were like batting around, like, okay, what should this rocket look like? I think I was literally in like Tom's kitchen or something, and we were like the spreadsheet, and like, okay, we need to like make a minimally viable rocket, like half a ton or whatever, something like that. And then initially the spreadsheet had we had an NTO MMH upper stage, so hypergoal upper stage, kind of like a variant of the TRW Lundy.
Yep.
So.
Which I think Tom worked on, right?
Yeah. Well, Tom, people who trained Tom worked on it. He's not that old.
Yeah, that's right.
It was like a baby, you know.
Yeah.
It was a very advanced
He
baby.
designed it.
But his mentors did work on Limbee. So, lunar module send engine. So, basically a pintle injector.
Right, that's where the pintle injector comes
Yeah,
in, right?
you can also dethrottle it and everything. So, is, how much does anti-MMH cost? Oh, it's super expensive. Okay, it's like a rare chemical. So even if you're like, you know, if Edison and Tesla had a baby and that baby was smaller than both of them combined and said your job is to optimize an NTO-MMH upper stage, you're screwed. Okay. So, like nitrogen tetroxide and monomethylhydrazine are super expensive, and they're also toxic.
Super nasty, yeah.
Yeah, I mean,
handily costly. All are probably pretty
yeah.
efficient.
I mean, I do think like safety is overcorrected on the NTO-MMH. It went from like nobody had any protection and breathed the fumes all day to it's cyanide. Okay, and neither of those are true. It's not cyanide. You won't die. And Bill Gusmeyer told me like a story of like when he started at NASA, they actually I think passed around like a cup of like hydrazine so that everyone knew what hydrazine smelled like. So like because it has like a rotten egg smell or something like that. So it literally an open cup of hydrazine, and like obviously he's still alive. So so that's an example of like don't optimize the thing that shouldn't exist. We should not have NTO-MMH upper stage. Right. Now Dragon does have that, but that's because Dragon's going to do a lot of like nuanced firings of the Draco engines, with duration with pulse durations, and if you have trying to have something that's not hypergolic is very difficult, and it can be done. Like, but you can say not hypergolic and not cryogenic. Now your options tend to suck. Yeah. So they start going down the peroxide, blocking up the peroxide tree or something like that, and that's or super esoteric monoprops. Right. And that's like again back to big money. So. Yeah.
That's step 3.
Yeah, so, exactly. So getting through these is quite laborious. Sorry for the laborious explanation here, but and then finally you get to step 4, which is accelerate cycle time. If you're moving too slowly, go faster. But don't go faster until you have worked on the other 3 things first. But if you're digging, and your grave, don't dig it faster. Stop digging your grave. Right. But you can always make things go faster. And then the final step is automate. Now I personally made the mistake of going backwards on all 5 steps, multiple times. So I have to repeat this, yes, multiple times on all 3. Where, let's say, I automated, accelerated, simplified, and then deleted. Like one example I talked about before is like there were these like fiberglass mats on top of the Model 3 battery pack that were in between the full pan and the battery. And it was the 1-point choke in the battery pack production line, and I was like basically living on the battery pack production line, like trying to fix the line. Because it was like choking the entire Model 3 production program. So the first mistake was we should not have. I like try to fix the automation, like make the robot better, make it like robot move faster, a shorter path, increase the torque, delete the reverse 728 degrees on the bolt because that's unnecessary. Just go forward fast, not at 20% rate and 100% rate. Instead of spackling glue on the entire battery pack, just put little dabs of glue because the fiberglass mats are sandwiched between the battery pack and the floor pan anyway. So all you need is like something to hold them in place until you bolt the battery pack into the car. So automating was a mistake. Then accelerating was a mistake. Then optimizing was a mistake. And finally, I said, "What the hell are these mats for?" And I asked the battery safety team. Because are these mats for, what are these mats for? They said, these mats, I said, they're for fire protection or something? They said, no, they're for noise and vibration. So you don't get that, and I said, but you're the battery department. Then I asked the NVH, Noise Vibration Harkness team, what's it for? They said fire safety. So literally, it was like being in a Dilbert cartoon, okay? It was like, actually, I feel like I'm in a Dilbert cartoon quite frequently. So I'm like, are we in some simulation where I'm trapped in some like Kafkaesque / Gilbert cartoon situation, but that's what it feels like a lot. So then finally, okay, great. Let's try a car with the fiberglass mats and without, and they put a microphone in both, and see if you can tell the difference. You cannot. You cannot tell. In fact, I was like, which one is which? So we just deleted them. And just bypassed this $2 million robot cell. It was just a complete pile of nonsense. Another mistake that has happened in production is too much in-process testing. So when you're first setting up a production line, you don't know where things are breaking. You don't know where things are breaking. So you'll test work in process at various steps. And because you want to isolate where's the mistake occurring. So a very common mistake issue with production lines is to have is to not remove the in-process testing after you diagnose where the problems are. So basically, if you have like very high acceptance, if things are getting to end-of-line testing and are passing, then you don't need to do in-process testing. So. But what tends to happen is there'll be an initial development engineering team that will be basically debugging the production line. But then they will forget to take out the in-process testing steps. So then what happens is the in-process tester will often choke the cycle time, choke the line production time. It'll be like the limiter. It'll also have some number of false positives and false negatives. But I mean, it'll be like false positives, then you're rejecting good parts.
Right.
So really in volume production, if you have if things are working well, you're really just taking a risk. Will this subsystem be rejected during the production process or at the end? And so you just really want to move things pretty much almost always to just test at the end line, and that's it. Maybe there's like one or two in-process steps that are hard to test at the end of the line, but basically remove almost everything. There's another thing with battery pack where this is so crazy. One of the things the battery pack has to do is resist water ingress, so it has to be leak proof. So if you drive through deep water, water doesn't come into the battery pack, it's short out the battery pack. You might have seen some of the videos of people driving Teslas in flooded water, where it's China, half underwater. Yeah, there was literally a guy, I believe in Kazakhstan, literally drove a Model S through a submerged water tunnel. It was, all the other cars were out, and he basically steered the car with the wheels and used the wheel rotation to like a boat and drove out the tunnel. So this is important to have the battery pack resist water ingress. But then instead of us doing a pressure test on the battery pack, we're actually pressurizing the inside of the battery pack, which was the wrong direction. And the battery pack lid was glued, was basically had resin that was not cured, and so we were just blurting out the resin, which doesn't make any damn sense. Right. Because you should actually be drawing a vacuum on the pack, and not pressurizing it. Right. And especially not pressurizing it when this uncured resin is what's holding down the battery pack. Yeah. So the pack was failing quite often on the pressurization test, which should have been a vacuum test. Anyway.
Speaking of Gridfin.
Yeah, great.
Look at that. Man, that thing is huge.
Yeah, that's what I said. It's like a dinosaur bear trap.
Oh wait, that'd be just a dinosaur trap, wouldn't it?
It's a dinosaur trap.
That's insane.
Yeah.
Honestly,
this thing has got the T-Rex.
Oh my gosh, that's crazy. And of course, it's got the serrated teeth, which help in the transonic regimes, right?
Yeah.
Is there any other reason for the teeth other than that?
No, it just well, it actually helps in transonic and subsonic, but Yeah, the effectiveness is better if you've got a pointy, full pointy, basically. There is a limit to its pointiness. Sorry. Hey, Robert. So, yeah, exactly. It's crushed under a better. Under.
Wow. So how heavy are these guys?
Man, these are. I started to think. Actually, I don't know the number offhand, but probably at least 3 tons. I'm guessing. So I'm holding it. And this is not. This is why, like, when it says like moving target, this is not the. Like, I wouldn't take this to the bank. Like, it's not. You know. There's quite a lot of mass we can get out of this.
Right. Yours is just good enough for now. Like that's
yeah, it's good enough for now. But like we basically just need like enough control authority to get this through the atmosphere and position well enough so that when the engine's light, the engine can correct whatever error is left after the that we couldn't take out with the grip fins.
right. Man, that is crazy. Those are huge.
Yeah.
And so it looks like the motor will mount to that lever arm there. Is that just a?
Yeah. So this is there's a motor that's this will basically be this will react onto the dome, basically the fuel dome. So there's like kind of like a C channel around the fuel dome itself, and there's a motor that's going to rotate this with a gearbox, and that's basically the load will be reacted between the circular feature that you see there and the sort of I should say C channel, sort of L channel on the dome. So it's just a simple sort of ring on the dome.
And then is that so? What I'm seeing there, where there's the ropes actually through on the end here, is that the lever arm for the thing, or is that just a?
Yeah.
Wow.
So
I see it slides over. It's like a.
Yeah.
Okay.
That's basically that's where the motor will interact. So it's yeah. Wow. But it's just basically we're just using like Model 3 motors basically.
Yeah. Which is so cool.
Yeah. So yeah, might as well use it.
So you mentioned you're really trying to simplify it. There's been talks that they're not. Did you say on Twitter that you weren't going to have you're going to eliminate cold gas thrusters or hot gas thrusters on the B4 for the first orbital test?
Yeah. Well, we can move to like maybe a more quieter location.
Yeah.
Isn't it nice when things are as good as gold? You know, when your fave spot is always nice. And your usual? Perfect. Dating matches always match there.
I mean, I'm pretty sure we can cut the weight of that in half. Like that's, we're not even really trying to optimize the gauge. That's just basically plate. Yeah. So that's just like cut plate, right? Welded together. So this is gonna like make the damn thing work, and then we'll optimize it.
Yeah, of course. Which again, some of the Soviet Union was so good. That was like minimum viable product, basically. Get it good enough to fly and test. And obviously, you guys did have a Starship big time with the 8, 9, 10, 11, 15. Was like, let's just get it out there, see what works, see what doesn't, and iterate.
Yeah, and if you look at like the various reasons, like where we blew up Starships, like, and you looked at the risk list, none of the reasons it blew up were on the risk list.
Really?
Yeah, there was like no. Maybe you could argue like one of them maybe was on somebody's risk list, but it wasn't brought up beforehand.
Right.
That way.
Right.
So. I mean, there's a crazy amount of new technology happening here, and it's all evolving simultaneously, so we need to iron out, like, the unknowns, so to speak.
Yeah, the unknowns are the big ones. And we got is that the new flaps for 20 down there?
Yeah.
numbering scheme, because you were talking about version 2 Raptor the other day. What we've seen so far, are those version 2 yet? Like the green nozzles, those aren't version 2 yet, right? Have you started making version 2?
We made parts of version 2. So we're gonna make the first camera assembly. We made the first camera assembly, and we have, I think, pretty much finished the design of the pumps. We're gonna make the pumps. So hopefully we'll have, I don't know, Raptor 2. You know, in about a month we might be testing the first one.
Okay.
So,
and will that be? You said you're still going to be kind of producing stuff, or the prototypes are kind of going to be always in Hawthorne, then eventually you're going to be moving mass production to McGregor.
yeah, we're doing volume production of Raptor and McGregor, but we'll keep California factory operating basically for development engines and the Raptor vacuum version.
Yeah, Ram Pack.
So yeah.
Yeah. So if you're reaching 230 ton on version 2, what bar are you going to be? What's that going to be at? Like
That's a 300.
300 is
Technically, I think 298, but I think we should. Come on, we gotta like get 2 more bar out of that thing.
Yeah.
So.
Wait. So even only 300, big air quotes on 300. You're getting 230 already?
Yeah, but then we're opening the throats and reducing the area ratio.
Okay.
So the extra thrust is like there's a slight. I think we lose like 2 or 3 seconds of ISP, but we gain a lot more in thrust.
Yeah.
And the increase in thrust outweighs the slight drop in ISP.
Yeah, especially on the first stage.
Yeah.
Yeah. Well, what's the?
I mean, basically, any thrust weight below 1 is worthless.
It's worthless. Yeah.
Yeah.
So if you go from 0.4 to 0.5, it's a massive leap compared to even. Yeah. Yeah. Okay, that makes total sense. So the Rat Pack, what's that for thrust? Is it still around that same number, about 200 tons? But
No, the Raptor vacuum water bag, we'll call it, will actually be the 230 ton thrust number is the thrust at sea level of the sea level version of the. It's essentially like helpful to, and like some people like quibble about like why are you talking about thrust in tons? That's not technically a scientific thing. It's because you can do the math in your head really easily if you have a rocket in tons and thrust in tons.
right, of course.
That's why. And Newton's going to like divide by 10 all the time.
Right.
This is like annoying.
Yeah.
And then you only get kilograms. Now you got to like divide by 10,000 to get tons. This is ridiculous.
Yeah, it is.
Okay, so you're like, what? This is absurd.
Yeah.
Only a fool would use Newtons, in my opinion, for designing a rocket. And especially big rockets, because you just like have a zillion newtons. So
Yeah.
But if you measure things in tons and you measure thrust in tons, now you know thrust to weight very easily.
Right.
So
Now, is that like the only imperial thing you measure then?
no, these are
Still
all
metric tons.
Metric tons.
Okay.
Yeah.
That makes sense. Okay. I was
Yeah,
getting
no,
nervous for a second. I was
pressure is in bar,
Yep.
and because everybody kind of knows like what's 1 atmosphere.
Yeah.
So
Yeah.
and pascals is another trash unit. I hate pascals. So why is it so tiny? It's absurd.
Right. We should have a whole segment of units that Elon hates, and it's just.
And it's like units that make understanding things more harder instead
Yeah.
of easier.
Yeah.
If everyone understands like bar or an atmosphere essentially, and everyone understands like people can get their mind around a ton, like you have
Right.
intuitive sense for a ton.
Yeah.
Okay, like a car is like 2 tons.
Yeah.
Sure.
Yeah.
Like,
You
can't
have
pick that
some
up.
grasp. You have some
Yeah.
context.
Yeah.
For
If you
it.
got hit by a ton, you'd know what that meant. If you got hit by a Pascal, it's like, I don't know, mouse fart. It's like 1 Pascal.
Right.
So, because it's another important principle, which is that you really want everyone to be chief engineer. So that everyone is chief engineer means that people need to understand the system at a high level to know what they're when they are making a bad optimization. It's like when they are say because we've done this many times where we've like put immense effort into reducing engine mass, but hardly any effort into reducing propellant residuals, or like order of magnitude less effort into reducing propellant residuals, and then you land with a literal ton of unused fuel. And actually, we still kind of do that with Falcon 9. It has about a ton of unused fuel upon landing, which is pretty annoying.
Right. Well, that's still not much in the grand scheme of everything. It's still not much, but that is, in context, though, it still is quite a bit, though.
Yeah, but like we've spent so much effort getting a ton out of engines. Like, you know, that's sort of whatever, like 130 kilograms per engine. Like that's 100, yeah. So 120-ish. So yeah.
Like, the sunsets out here are pretty hard to beat. That's insane. Amazing. So, congrats on the HLS. Solidifying a little more today.
That was cool. Gino is a staunch defender of good contracting.
Can we head over and check out the mock-up there? Because there's still a lot that we don't know about HLS, publicly at least. I assume that you know a decent amount more.
I don't know if I do, but
Well, first off, I'm excited about is those thrusters.
oh yeah, okay, so yeah, so thrusters are a good example of running that algorithm I just mentioned, laboriously mentioned, which is a question of requirements. They get regular requirements done, meet the parts.
Yep.
So when looking at what does the booster actually need to do with stage separation, if you put rotation into the stack before you set off the main engines, so they're both rotating. They're gonna rotate.
Wait, sorry, like pitching, yaw,
Yeah,
or
so
like
you got the integrated stack.
Yeah.
We do this with
Starlink.
With Starlink.
Yes.
So we rotate the stage.
Okay.
And
It kind of flings it out.
yes, but they basically have different amounts of inertia.
I can see the comments now.
Linear inertia. So they basically move at different rates. So if you rotate the thing, depending on where you are, you will move at a different speed.
Oh, I can see the comments now.
Separates if you rotate and then separate. So there's no actual separation mechanism for the Starlink satellites. And they technically can bump into each other, and occasionally do. But if they bump into each other for like 1 mile an hour, it doesn't matter.
Right.
So this balance will be
Through the pretty hard environment of launch.
yeah, it's fine. So, but I'm pretty sure like this might be the only we were like literally tossing 60 satellites off with like a bundle of hay, like
Yeah.
dumping the rods that hold them down.
Yeah.
Like a hay bale, and just flinging them. And it's fine. So they just separate, boot up, and go to their position. So,
Excuse me.
with the stage step, instead of asking the attitude control thrusters, the reaction control thrusters to do the booster rotation, which is a lot of force, you have the main engines initiate rotation.
Yeah.
Now this is quite complex space ballet, because everything's got to happen in just the right way. But you basically initiate the rotation of the stack, stop the main engines, then the two will actually separate by themselves.
Yeah.
And you need like a little bit of. We have like call gas. ACS or reaction control system. It's like depending on who you ask, it's a reaction control system or an attitude control system.
Right.
It's basically like small maneuver.
With advanced tech and safety features as standard, owners don't want just anyone knowing about the Suzuki Swift. Suzuki, good different. Step into your future with learning that can take you anywhere.
Is it really on the side?
All by yourself. Listen to everybody say, be everybody else. Can't you see?
Thank you, Your Honor. The case is very, very simple.
Ain't nobody just like
The Open University.
me.
The future is open.
Vincent's new electronics category means tech is new again. And with our optional electronics bed,
Ring thrusters. So you fire those on the ship. That gives you a little bit of maneuvering. And then on the booster, we actually have quite a lot of ullage gas. Like basically you've got a lot of hot gaseous oxygen and hot methane, which actually have, if you've got a big enough area, it's got decent thrust and vacuum.
The actual
The vent.
just
So
literally.
literally used to vent the stage.
Yeah, so not in a separate hot gas bottle, but literally like the ullage of the main tanks.
Yes.
Okay.
So just use the ullage as your thrusters, and just control the orientation of the venting, so it is not just venting out sideways, but it is venting in a direction that is useful. So, which can be sideways sometimes. Anyway, we've got like basically a lot of gas in this thing, and which would have to actually just vent to vacuum anyway, because it's got too much gas.
Yeah.
And that's just extra mass that you don't need.
Right.
So, so then if you've got basically enough control authority because of the kicking the whole stack over before main engine cutoff, plus using the ullage gas to vent, then you don't need a separate hot gas thruster system. You don't even need a cold gas thruster system. You already have hot gas.
For the
This
booster,
is
right?
to meet
Only.
the question requirements to lead the part.
Yes.
Yes.
But this is only for the booster, right?
Yes. Although arguably, now you mentioned it, we might be wise to do this for the ship too.
How can you have? You'd think that because
At least mostly.
well, the tanks are what, 6 or 8 bar or something? The main tanks.
Yeah, they'll be like six-ish bar.
Okay, and so wouldn't those be pretty low pressure, low ISP gas thrusters if you're only doing the gas from there? Or is there some trick you can do to?
No, in vacuum, you don't it's different in atmosphere. So, like 6 bar in vacuum is actually decent. Like it's like common to have thrusters, in-space thrusters that are let's say 8 bar. Like the Draco thrusters for that maneuver Dragon are operating around chamber pressure of around 8 or 9 bar.
What?
Yeah,
Really?
you don't need like Dragon's still in PSI, so it's like 120 to 130 PSI. Technically, it's a pressure pulse, but
Right.
it's so 120 PSI is like roughly 8 bar ish, maybe 8.5 bar. So it's not that far from the tank pressure.
Right. So you don't even need to store the gas in an even higher, like in a bottle, it's at like 200 bar or something. You don't even need to do that to operate RCS.
No, if you've got hot gas, first of all, we really want the ullage gas to be as hot as possible, up to the point where it is impacting the strength of the hull. Like we don't want to soften the metal so much that it pops, basically.
Right.
The hotter the gas is, the higher the ISP. So having hot gas is good, and it's already there, and you already have the pressure vessel,
Right.
and you're gonna chuck it away anyway.
Yeah.
So obviously just use it as additive control.
So
Obviously, now initially you can't do this with the ship because everything's cryo. But once the ship is mostly empty, and it's delivered to orbit, it also is in the same situation with a lot of hot gas.
Yeah.
So actually, we should really be the vast majority of our maneuvering should be with the hot gas that's in the ship. I think now that we're gonna fix that.
Jeez. That's, but yeah, okay, so the thrusters on HLS that are going to be around the ring, the render showed like 24 or something of like, you know, the landing.
No, those are different. That's for landing on the moon.
Okay, yeah. Are those pressure fed? Like, what are those? Do you have a name for them yet or anything?
Let's just say like this is the tentative design right now, but with the agreement of NASA, I think we may see that design evolve, and it may be better actually.
Right.
So, like a big question here is like, can you land on the moon with the main engines? Or do you need a separate thruster system that's way up there? Like basically, if you land with the main engine, are you going to dig a big ditch in the moon and then fall over because you landed in a ditch that you dug?
And you shot
It's like literally dig your own grave.
Yeah.
That would be obviously bad. You know?
Right.
So we don't want to dig our own grave and then fall in it.
Right.
But more analysis is like I think we could probably land with the main engine and not dig a grave and die in it. But we would have to prove that, get something that's like, I don't know, the consistency of like lunar regolith and like something that's like a good analog of that, and then like land a ship in that and see how big is the hole that would be.
Yeah.
If you've got low pressure engines that are high up, naturally you're gonna have you're not going to dig a hole, basically.
Right.
So that's kind of like the sure thing. But I think if we can prove that the main engines do not dig a giant hole, then we could land with the main engines, and then not have
any of those.
Yeah.
The ring.
Yeah.
What about the? Are you gonna have any sea level Raptors on the lunar variant, or will you only have vacuum optimized? Because I assume like on a normal starship, even at stage separation, you'll probably light all 6 at first just to minimize gravity loss or something, right? So you'll still fire all 6, then probably shut down the sea levels and let the vacuum optimize, like they probably do what, like half the second stage burn time or something with sea level, or have you?
So the vacuum engines don't gimbal.
Yep.
So you'd have to have something to provide the control authority. I mean, technically, you could say like, well, if you're in a low disturbance situation, like the moon has no atmosphere.
Right.
Man, this is beeping city. Yeah. So if you're not facing like a lot of atmospheric disturbances, then you need much less control authority, and you could probably land with 3 just by differential throttling of 3 engines.
Yeah.
But if you lost any of the engines, you'd be toast.
Yeah.
So probably makes sense to, I don't know, probably keep the same config,
Or like you could even just have 1 in the middle that would offer, a decent amount of gimbal authority and all that.
It depends on how much optimization we're aiming for here.
Right. Because you're only probably gonna make 1 of these things, right? Or are you planning on like, is NASA wanting multiple, or oh my word? So by the way, I think there's a good chance that ITAR and comms might not want all of this. Wait until you see part 2. It is unbelievable. And I promise I'm going to get it to you as soon as I can. Thank you, Elon, for spending so much time with me and allowing me to ask all of the questions I had. It was amazing. And thanks to the teams at SpaceX for allowing me to share this all with you. And thanks to Cosmic Perspective for helping shoot this and just kind of helping out all the time. Find them on YouTube and on Patreon as well. And I owe a huge thank you to my Patreon supporters for helping make this and everything else we do here at Everyday Astronaut possible. If you want access to our Discord channel, where we'll probably end up talking about this conversation a lot, or live streams, or lots of other fun stuff, head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome web store. We can find shirts like this, the R7/Semi-Orca/ the predecessor to Soyuz, new shirt that we have that is awesome, as well as our new Mars hats. But you can also find some classics like the Full Flow Stage Combustion Cycle shirt and hoodie, and the Future Martian shirt, and schematics collection, and lots of other fun stuff. So head on over to everydayastronaut.com/shop. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.
What's something your ex would say about you? The laugh. They're laughing at me.
Hi, it's me, Tim Dodd, the Everyday Astronaut. EverydayAstronaut.com. All right, let's go check out some Raptor engines. So, by the way, I think there's a good chance that ITAR and comms might not want all
Yeah,
this.
just like, you know, it just can't be any more than people are already getting from
That's true.
telephoto lenses.
That's which is pretty much
And
everything.
frankly, if some fool wants to copy this design, go for it. I mean, Raptor 2 is a giant improvement over this. So,
What's like the big simplifications you're hoping to have?
oh, maybe I shouldn't tell you all the secrets. We have like funny things on the good Pikachu over there.
I love that.
Hello again.
Hello again. So that probably, I assume that means it's flown? Is that a flown one?
I don't know if this one's been flown.
Jeez. This really does look like that thing with all the NK-33s. You know, those
Yeah,
videos
exactly.
that
Like the engines discovered from engines that came back from the cold.
Yes, it seriously, literally looks like that. This is insane. And the man, that rat is big. Jeez.
Yeah, I won't tell you all the secrets, but just like you will be able to see the difference very clearly.
Okay.
And I guess since the engines are, it's hard to have people not see them.
Yeah.
They will. You will. It's the Raptor 2 is visibly cleaner than Raptor 1. Like it's this this sort of maze of plumbing and wiring doesn't exist on Raptor 2.
Although it's already slimmed down a ton from like you know the.
It used to look like a friggin' Christmas tree.
Yeah.
Like you couldn't even see the engine for all the stuff that was
No,
around
you
it.
really couldn't. And now it's like, especially around the turbines and stuff and the pre-burners, it's. I mean, that used to be a whole. There's sensors every 2 millimeters.
Yes.
So, RapVac or RaptorVac has its own regen channel on the extension. It looks like.
Yeah, that's a steel tube wall, gray steel tube wall.
That looks good. And it has a different profile too. That actually looks like the initial exit. Is there a different throat in it and everything, or
No,
is it?
throat's the same.
Throat's the same.
It's just the part after the throat that's the diverging section has a different angle. It's basically following a route contour for a higher expansion ratio.
Yeah, yeah. What is expansion ratio again? Is it like 150 or something?
No. Man, I think we're so this is actually there's I think we're around 80-ish.
Oh, okay.
But we want to do a little bit better, maybe 90. So
Because you're already doing like 380 ISP out of that thing, aren't you? Or, I mean, sorry, yeah, 380.
380 is the aspirational number.
Okay.
But we should be. I think we'll get like 377 or 378.
Okay.
So,
okay. And how are those coming along? It looks like obviously you've got a third one here. You've obviously made at least 3.
Yeah.
And there's obviously S20 is going to have 3.
Yes.
Yes.
So,
Jeez.
but for Raptor, all the engines will have the same pumps and thrust chamber assembly. So it's really just they'll be one one variant that has a big nozzle and one variant that doesn't have thrust vector control actuators.
Okay. Okay. So that's going to be the difference between the R boost and the.
Yeah, I mean it's basically the same engine minus PVC.
Gotcha. So the outer shells that you're working on for the GSE are 12 meters.
So there's a Raptor without the stuff, looks practically naked.
You're like, actually, that's secretly version 2. It's super simple. No.
Version 2 will look a bit like that, actually.
Really?
It's very tight.
Really? I mean, again, kind of when you look at some of those Soviet engines, they were also like incredibly simple looking. I'm guessing they just obviously didn't have them wired to the gills with electronics though either, you know?
They simply did. Back in those days, they did not have good electronics.
Right.
So there's nothing to.
There's nothing to wire.
Yeah.
Is how much like I feel like you iterate this quite a bit and remind people that it's failure kind of is an option. Why do you think people are so afraid to fail, and why do you embrace it, or how do you teach that culture even that it's okay when you're not even trying to, like, you know, SN8 is a perfect example. You weren't trying to like do a mission. You're just trying to get data out of the thing.
Yeah. We have just a fundamentally different optimization for Starship versus, say, like the polar extreme would be Dragon. Like Dragon, there can be no failures ever. Everything's going to be tested to, you know, 6 ways to Sunday. There has to be tons of margin. There can never be a failure ever for any reason whatsoever.
Yeah.
There cannot be, we can't be, so that's like extreme conservatism.
Mm-hmm.
Then Falcon is a little less conservative. It is possible for us to have, say, a failure of the booster on landing. That's not the end of the world.
Right.
And then for Starships is like the polar opposite of Dragon. We're iterating rapidly in order to create the first ever fully reusable rocket, orbital rocket.
Mm-hmm.
And fully and rapidly reusable. Reusable in a way that is like an aircraft.
Mm-hmm.
So rapidly reusable rockets.
It's a big deal.
Yeah. That's the fundamental holy grail for making life multiplanetary.
Where do you think the space shuttle failed in being, in any, definitely rapidly would be a word you got to scratch off the list.
Yeah.
And refurbishable might be a
Definitely
better word. But where do you think it failed, and where do you think, like, what lessons have you learned that you know you're not going to be making on Starship?
Space Shuttle had almost no room for iteration because there were people on board. So you can be blown up shuttles.
Yeah.
So that's a big problem.
Yeah. Well, they did very, very little iteration. I mean, yeah, like
very little. In fact, lack of iteration was the problem.
Yeah.
Because a lot of the issues they were aware of, but people were too afraid to make change.
Because design throws.
Yeah, because it's like, yeah, I mean, there was risk-reward asymmetry.
Mm-hmm.
So, big punishment for if you make a change and something goes wrong, big punishment. If you make a change and it goes right, small reward.
Yep, yep.
So, the issues with the O-ring and then with the insulation coming off and hitting the wing were, they've seen this before.
Yeah, they were known.
There are known issues.
Yeah.
So, because it had worked before, they're like, well, it worked before. The Russian roulette works before.
Right.
So, look, I've pulled the trigger so many times. It must be no bullets.
Must be no problem.
Yeah. So, anyway, it's just it's hard to iterate though when people are on every mission. So, you can't just be blowing stuff up because you're going to kill people. Starship does not have anyone on board, so we can blow things up.
Yep.
That's really helpful.
Do you have any considerations yet on any kind of launch escape, or are you just hoping that by the time you put people on it, you've flown it, say 100 to 200 times, and you're familiar with all the failure modes, and you've mitigated it to a high degree of confidence, or what's your...
Yeah, launch escape, I think, is, you basically just need to fly a lot and have a lot of redundancy. So if you lose an engine on the booster, it doesn't matter, basically. If you lose multiple engines, it shouldn't matter. And you should be able to lose an engine on the ship, everything's okay. So, because launch escape is basically just protecting you for the ascent phase. And actually most launch escape systems only protect you for a small part of the ascent phase, because the typical launch escape system is a solid rocket motor on the tip of the capsule.
Yep.
Which then has to be
to be jettisoned.
It has to be jettisoned on every mission. So if it's not jettisoned, the crew dies.
That's a failure mode right
It's
there.
a failure mode.
Yeah.
So you have a state change post liftoff, which is bad. Then because the damn thing's so heavy, they also can't carry it all the way to orbit. So they'll typically jettison the escape system shortly after second stage ignition.
Yep.
Or final stage ignition.
Yeah.
So then you don't have escape all the way to orbit either. Now, at least with Dragon, we have escape all the way to orbit. So that's like, I think, safety improvement.
Yeah.
But then you know, there's no escape system coming back to Earth. Like, that doesn't exist.
Right.
And then you can't have an escape system on the Moon or on Mars.
Or on Mars, yeah.
Yeah, so, like, you can't have something pop off and then have chutes drop. There's no atmosphere.
Right.
And then Mars has very low density atmosphere, so
Yeah.
they'll just like hit the ground supersonic, you know?
Right.
They're not gonna save you. So the ship has to be safe enough for people without an escape system.
Right.
Because otherwise you can't go to the Moon, can't go to Mars.
Right.
So
you
it's
might as
pointless to do it on Earth.
Well,
it just fly a lot.
Right, and that, I mean, I never really thought about that, you know, you're going to be, you're going to be flying so much without fear of retribution of failure, that, unlike the shuttle, like you mentioned, I just never really considered that, you know?
Yeah.
So, let's see. What is, those are the vacuum mounts, aren't they?
Yeah.
Wow, that's cool.
Yeah. I mean, this is stuff like very much version 1. So
Yep.
it could be.
Don't despair about motor repairs. With up to £250 excess refund reward on car insurance.
Marketers, stop missing deadlines for high-volume campaigns like Black Friday, Valentine's Day, or holiday sales. With Storytext batch creation, you can make high-volume ad production fast and easy. How does it work? You create one master template, and with just a few clicks, generate hundreds of variations in bulk. No more last-minute rush. Launch your marketing campaigns on time, every time. Book a demo today and see how you can accelerate your campaigns with Storytext.
It'll be a lot better with the next iteration.
Well, a lot of people ask me, you know, like, hey, I want to start a YouTube video, where do I start? And I'll be like, start. You just have to start. And I kind of feel like this is a similar philosophy. It's like, you're not going to know what's wrong or how to make it better until you do it at least once anyway, you know? And you just simply have to start. You have to force yourself to start.
Yeah.
And then, yeah, that's, then you improve from there.
Exactly.
Man, are you pretty used to the heat? I feel like it's pretty hot out here.
It is hot. I mean, this is the worst. This is like summer, you know. So
right.
That's just like the worst of it.
Yeah.
It's not that bad. You think like just pretend you're in Hawaii.
Right. There you go. So speaking of shuttle,
I mean, I think it's a cool view.
Oh, it's a really cool view. Oh, and thermal protection. It seems like you guys have made some. I mean, it looks like S20 is going to be pretty well decked out in the stuff. How are you feeling about the thermal protection system? You think that's a pretty good solution?
We'll find out.
Have they been holding up pretty good, at least on the low altitude stuff, as far as the mounting points and stuff like that?
It hasn't full. I mean, it's still there. I mean, you can see the videos.
Yeah.
It takes off with the tiles and it lands with the tiles.
Yeah.
And we have, I think, a good attach mechanism, which seems like a good attach mechanism. because it allows. It's just mechanically attached with some play in the tiles, so the tile can move a little bit. It's quite a tricky thing with the tiles because the tiles are essentially ceramic,
Right.
And they're attached to a metal substructure that is changing in temperature dramatically. So it'll be room temperature right now, then it'll drop to cryo temperature when it's loaded with cryogenic propellants. Then it will be heated up with hot ullage gas.
Yep.
So now it'll be way above room temperature. Then it'll cool down. Then the tiles themselves will get hot on re-entry, and they also have some expansion.
Yep.
So there's a lot of expanding and contracting going on all over the place. So I think one of the big questions is, are these tiles, are we going to have a crack or a gap in the tiles? Like if they bang into each other, the ceramics, like a coffee cup, is ceramic. So if you bang two coffee cups together, that's usually bad.
Okay. Yeah.
So if we if the tiles bang each other and a crack, this could result in a failure on entry. So I think there's like a huge question of like, when we get the ship to orbit, how is it able to make it back through Earth's atmosphere? Because it's coming like a meteor.
Right.
You know, it's like a blazing hot meteor. Will the heat shield stand up to it, or if there's any crack in the armor, it's toast.
Yeah. Yeah.
So hopefully we at least find out where the crack in the armor is.
Right,
That would be great.
And then if you have to, you can make some thicker or smaller, iterate to that degree of where you find those failures again.
Yes.
How will you know? Like, what if something just goes? What if the first orbital attempt just goes totally, doesn't even make it in for re-entry? It's just a million pieces at the bottom of the ocean. How will you know where it failed?
We have temperature sensors.
Nice.
We'll probably need like some thermal images inside the tanks. So just like IR cameras.
So you can see if certain specs was getting real hot.
Yeah, IR cameras on the inside will show you what the backside temperature is.
Yeah, let you know if a leak
like something will
propagated.
pop if the backside temperature. Like it was.
Right.
Frankly, I'm not sure. I take it back. If you just have a camera,
you'll know.
Visual.
Yeah.
You'll see is something glowing white hot. Okay, that's bad.
Yeah.
That's the bad part
Yeah.
right there. So you don't even need a thermal image, frankly.
Yeah.
The steel will glow white hot before it melts.
Right.
So
You'll know.
you'll know. It's so subtle.
And the very first orbital test, it kind of seems like there's been a lot of debate of like, is it going to orbit and deorbiting, or is it just orbital velocity with a low perigee that's inside the atmosphere, and that's how it'll deorbit? Like, will it?
No, it's getting to orbital velocity, but but it's not circularizing its perigee.
Yes.
So it basically goes like 3/4 of the way around the Earth, but because we didn't raise the perigee, the atmospheric drag will pull it in.
Yep. And the velocity will probably be greater. Re-entry velocity will be greater that way, or similar.
Similar.
Yeah.
It's not a huge difference. But it basically it could easily, like, if you just pop like the attitude control thrusters or like the ullage gas alone could put it into orbit. So like raising perigee slightly is easy.
Yeah.
It's like remarkably easy. So you just want to raise it like a little bit.
Are you hoping to actually recover the first one, or like
No.
trying to even land, or any? I mean, is it going to fire its
The first one
engines?
is for the first orbital launch. Our goal is to make it to orbit without blowing up.
Yeah.
That's our goal.
Yep.
And frankly, if we even get if the booster even does its job and something goes wrong with the ship, I still count that as good progress.
Yeah.
Like basically, actually, to be totally frank, if it takes off without blowing up
Right.
blowing up the stand, the stage 0, which is much harder to replace than the booster, that would be a victory. The things do not blow up on the stand. That's what I'm more concerned.
But you keep calling you calling the stand stage 0?
The launch system.
Really?
Yeah.
Huh. The ground G, I see the tower and all that stuff.
Stage 0, yeah.
Okay. Yeah. I get so spoiled now with again Soviet nomenclature. It's like there's 0 for like the boosters, so it was
Really?
like core is 1.
Okay.
And then what I would call opposite. The boosters are 1, core is 2, but like the next upper stage, or what I would consider stage 2, is stage 3. So it's really confusing, and I kept being like, oh yeah, third, second stage, and they're like, no, that's third stage,
So stage 0, the launch system,
Yeah.
the launch mount, the flame diverter,
Yep.
sort of,
Yep.
sort of, the big tower,
Yeah.
the propellant farm, and all that's basically, all the lines and everything. That's stage 0, and it's very hard.
Yeah.
It's harder for us to make a stage 0 than to make a booster or a ship.
Okay.
So
Hopefully it doesn't blow.
yes, that would be great. And then, like, the best case outcome for the first flight would be that the booster does its job and also is able to relight the engines, and it's going to splash down.
Yep.
In the Gulf.
Only like 20 miles out or something, right?
Yeah,
Or
not far.
relative?
And then
With Vinted's new categories, you can now sell even more pre-loved items. Don't use it, sell it.
Who do I trust for business insurance?
If you need business insurance, join nearly 1 million customers who trust
ship or upper stage is going to come in just off the coast of Hawaii, near a military base there, and so we'll, splash down in the Pacific.
Mm-hmm. Yep.
So
So again, to reiterate, on the first launch, the booster, you're going to just use the gas venting to orient it for re-entry. It won't even do you will do a boost back burn though on the first one too, right?
let's just say it's an evolving situation.
Yeah.
In order to be 20 miles away, we definitely would have to do some kind of boost back, otherwise it's going to be way further.
Yep.
So, yeah, I mean, probably it's boost back, and then a propulse, and then basically want to simulate the landing, but not have it be too close to land, so it doesn't take out stage 0.
Right. Yep.
Yeah. So we want to say, like, can we position the booster precisely, such that if it had landed next to the tower, or if it had come to a halt next to the tower, could the arms have grabbed it?
Yes.
Mechazilla.
Yeah, Mechazilla.
Megazilla.
Megazilla?
Mecha?
Mechazilla. Okay.
Yeah.
Like a giant mech.
Mechazilla.
Yeah. What's the plan? Does it just come in and it sits then on the grid fins and or that little arrestor thing?
Those little tiny arms.
That tiny little T-Rex arm is gonna hold the.
Yes, there's 2 of them. But those things can take a lot of load.
And then it's just literally like a flat arm, kind of like this. That.
I mean, this is one of those things, like, it's hard to keep a secret when it's right there. People can just take zoomed up, drive past it, and take a high-res photo close up. So it's not exactly going to be top secret.
Right.
This is the first real big rocket development that's been so close to a public road that people are literally driving to the beach right past the launch site. So it's hard to keep a secret around here.
That brings up, I always keep wondering, like, we're seeing this insane pace, we're seeing all these crazy things happen. How much of that, like, is normal, at least as far as SpaceX goes, or how much of that is just because we're actually seeing it? Like, for instance, when you're developing Merlin and Falcon 9, were you blowing stuff up this much, doing things so crazy, fast-paced? Or is this, like, also fast-paced, but now we're also seeing it all, so it's hard to compare?
Well, I mean, this is definitely a case where we are washing our laundry in public.
Yeah.
And there's always dirty laundry in any program.
Mm-hmm.
It's really a question of whether it is seen or not.
Yeah.
Not is there dirty laundry.
Right.
Yeah. Every program's got dirty laundry, but in this case, it's in public. But this is also a case where we're intentionally iterating the design rapidly.
Yep.
And basically, ships and boosters will either be amazing lawn ornaments, which then have to be stored, and they look awesome.
Yeah.
But you know, we don't want 12 of them. It's gonna look bizarre, and where we would put them.
Yeah.
So, we, since we're making rapid iterations with each, almost with, basically every single ship and booster has had significant iterations. But you either want it to blow up, or the early ones, you want them to blow up, or you're going to have to find a place to store them.
Right.
So we actually want to push the envelope, and frankly, like if you don't push the envelope, you cannot achieve the goal of a fully and rapidly reusable rocket.
Yeah.
It's not possible.
Yeah.
You have to go close to the edge on margins.
Right. Right.
And there's a recursive factor to mass. So, like if you add, say, an extra ton of heat shielding, now you also need more propellant to get it to orbit. Right. And you need more propellant to deorbit it. And you need more propellant to land it.
Yes.
And the structure now has more load, so it's because it's carrying that extra ton of heat shield.
Yes.
So this applies to any given ton. There's a recursive value.
Yeah.
So in order to achieve the same payload, you have to, each ton is like basically almost like adding 2 tons when it's fully considered.
Definitely.
So I think we calculated it to be like a 1.8 factor, but I think it's probably we're forgetting something that's closer to 2.
Yeah.
So every 1 ton of mass begets an extra ton.
Yeah. Yeah.
So
what's, for instance, like what's S20's dry mass kind of looking like? What are you at right now? Are you like 120 tons? Or are you?
I actually don't know the exact mass of 20. We'll know it when we weigh it.
Yeah.
There's a lot of parts that have not been weighed.
Yeah.
So like, what is it actually? I mean, I hope it's not too insane. Ideally, it's dry. Its dry mass is hopefully not much more than 100 tons.
Really?
So, yes. But then you say like dry, do you mean not counting the air inside it?
Right.
Because by the way, the air air mass is non-trivial.
No, it's not.
This is a very giant volume. And then, do you mean dry? Do you mean with propeller residuals and ullage gas, which is at several atmospheres?
Right.
Which mass are you referring to?
Mass,
like sometimes in these things they'll play games with like where you say thrust away of a rocket engine. So thrust away the rocket engine with or without residuals. That's a big change.
Or with or without gimbal is something else that I've
exactly.
heard people kind of debate.
Yeah.
Yeah.
Merlin is, I'm pretty sure, by any standard, I think it's probably the best thrust weight of any engine.
Yeah.
Because it's like just so far, we really pushed the GD cycle engine to the, it's like A plus for GD cycle architecture, but GD cycle architecture is not an A plus architecture.
Right.
Full flow stage combustion, A plus architecture, but with a new architecture, we won't get an A plus within that. Like say in gymnastics, you like say how hard is your program,
right?
And then what grade do you get in the program?
Yeah.
That's kind of how the things work here. So,
what would you say version 2 is going to kind of come in at if you were to rate it?
I don't know. I'd say it's like B plus, something like that.
So good enough for now, but of course.
Yeah, Raptor 3, Raptor 4, Raptor 5.
Yeah.
By Raptor 5, it'll be an A plus.
Yeah.
So.
Yeah. Should we walk through here and check out what's going on in here? This is just a nose cone being assembled. It's not that it's showing
This is our new and improved nose cone.
Oh yeah, it's just straight. There's no cross section.
So this is if you look at that nose cone over there, that's made from stamped sections.
Yeah.
So you can see that's like 3 rows of stamped sections.
Yep.
This will be made of 2 rows of stretch form.
Wow.
So and you can see it's just way smoother.
Yeah.
This is just stretched over like a big mandrel. So just take a big sheet of steel, and you just stretch it over this giant tool.
Right.
So, and then you can have like things that are way bigger. Like you can't fit this in a stamping press.
Right.
This is way too big. That's like basically about as long as you can fit in a stamping press. You cannot fit something that's giant in this. Well, you could technically make some totally special case stamping machine that doesn't exist.
Right.
But You only need one. Since you only need a single-sided, it doesn't have like indentations or anything. So you couldn't make a car body side this way, but you can make something with this level of symmetry that is basically you can do a one-sided die.
Okay.
So you can just stretch form it over a big mandrel.
And this isn't the cargo. It's not show. It's just not complete yet, but it has that opening on the one side. That's not because you're working on the door, the jaws yet, right?
Yeah, I actually stopped work on the door, the fairing door.
Okay.
Yeah, we're gonna focus on getting to orbit.
Yep.
We don't need a door.
Yep.
So it's like we need to be super focused on getting to orbit, then super focused on getting the ship back, then we can worry about doors.
Okay.
It's just like unnecessary complexity. So like, is the door necessary to solve the problem? No. Will we use this? Like the first 10 or more that get back from orbit, we probably won't fly them again.
Right.
Or maybe once or twice, but then they're going to be in storage. Like for Falcon 9, and even like the Block 5, so-called Block 5, which is more like version 7.
Yeah.
Really. But we don't even want to use the early Block 5s. So, like, even those are a pain in the ass, and we prefer to retire them. So, like, when we have, like, a mission that requires an expandable booster, we'll put an early Block 5. Because the early Block 5s are not as good as the later Block 5s.
Wow.
And they're more of a pain in the ass to get ready for flight.
Wow.
So the reality is, the early ones are going to be, I mean, it's one of it. Yeah, I mean, as good as one of gets. They will not be nearly as good as the ones that follow, so then why keep them flying?
They're not even going to be doing any, they're not going to be putting any payload up, they're not, you don't even need to
we're just going to retire the early ones anyway, so why have a door on a thing that's never going to fly satellites anyway?
Yeah. How is the butt-to-butt refueling going? Is that, because that's got to be a pretty early consideration, because you're probably going to want to start testing that.
No, that's,
no?
We're going to get to orbit and back first.
Okay.
We don't need orbital refilling. Unless you want to go going to the moon, you need orbital refilling. Going to Mars, you need orbital refilling. Delivering satellites to Earth orbit, you do not need orbital refilling.
Right.
So let's punt that to later.
Okay.
I'm not sure it'll be the butts, but it might be something that might, like the. We switched the propellants full drain lines to be side. So come out from the side.
Not up through the booster anymore?
Because I was adding a bunch of stuff to the booster,
Yeah.
and then we're flying it every time. So it's better, if you can move mass to the ground side, it's better to move mass to the ground side.
Right.
That's why we took the legs off the booster and have the tower catch it.
Are you thinking about doing a tower catch?
It sounds mad. I mean, yeah, I know it sounds insane. But when I suggested that, people thought I was lost my mind, which I'm like, maybe I have. But I think it might take a few kicks at the can, but we'll get it right.
Yeah.
And then it just the work that you have to do to pick up the booster and put it on the launch stand, this gigantic skyscraper thing, in high wind, like windy situations. It's very windy around here.
Yeah, it is.
To pick up this booster, you got to put it onto its stand with precision. Then you got to pick a ship up and put it up on top of that. So that means you've got to have a secondary arm to steady the booster, so it's not moving around all over the place.
Yeah.
And then while the sort of mechazal arms pick up the ship and put it on the booster.
Okay. So the Maxilla arms are the ones that are going to be picking up the ship, not the crane?
Okay, so it's very important to appreciate that everything you see here is a work in progress. Right. What is said last week may be untrue next week.
We've seen that a few times.
Yes, it could be that we're actually just literally mistaken, a miscommunication, any one of a number of things.
Yeah.
We just had a better idea. In the case of, like, for the first stacking, we're going to do that with a crane.
Yeah.
We will. So, yeah. Well, Marvin the Martian right there.
I love that.
So, the first one we're going to stack with the crane. Because otherwise we have to wait for all the mechanisms to work. So we're like assembling the arms and you know, basically putting Megazilla together. But in the meantime, we could be launching.
Right.
So let's not wait for the tower to be completed. We've got like the second biggest crane on Earth. Let's it's like we don't necessarily want to have the second biggest crane on Earth just sitting there forever.
Right.
But it can be there for the first stacking, and then from the first stacking, then we can figure out, you know, just like, do we have the hold downs? Do the hold downs work? You know, like, or the launch mounts, I should say.
Yeah.
So it's really quite a complicated launch mount. It's got like basically 20 mount points.
Right.
And you got to line those things up and then put the booster on it and have, you know, does it fit?
Mm-hmm.
Okay, it won't fit.
Right,
basically.
right.
Now we're going to adjust it.
Yeah.
Okay. That launch ring is 370 tons. So, and it's going to tweak, like you move it from one place to another, it tweaks.
Yeah.
You know, it doesn't stay exactly the same. So we're going to have to like jiggle it around a little bit, put in some shims and stuff, and fit the booster.
Yeah.
So we want to do that soon. We should be done with this booster, I don't know, next week.
Yeah.
So,
wow.
So then we want to mount the booster next week.
That's gonna be insane to see.
Yeah. We're gonna try to put the ring on the stand, the launch ring on the stand tomorrow.
Wow.
But we may not succeed. We'll see. So probably the second flight will use. I mean, it's very likely the second flight will use the tower.
Okay. Second flight. Oh, so the first flight might still just use the suborbital pad.
No, it's going to use the. It's going to use. It has to use the orbital pad. We can't. The orbital, the suborbital pad cannot take the full weight of the stack. It's going to get crushed, and it doesn't have enough height. So the rocket would blast itself in the face. It's too low and too weak.
Yeah. Okay.
So we got to launch it from the super beefy stand.
Yeah.
But we don't want to wait until everything's ready with the tower just to stack.
Okay. So how will you secure it then when it's stacked? Like, just drop the starship on top
of the crane holder
until it's launch time, and then.
No. We do need the QD arm to work.
Yeah. Oh, right. So that can be a stability thing.
Yeah, it's exactly. It holds it, it stabilizes it, and transfers propellant. If we don't have that, we can't load a prop in the on the ship.
Okay, so that has to be complete.
Yeah.
But not necessarily the arms and everything else going on at that point.
Yeah.
So
yeah,
at this point,
we're like I said, there's a lot of moving pieces here. So some of this could be ready in time. It's possible that the tower could be ready in time, in which case we'll use the tower.
Yeah.
But if the tower's not ready in time, we'll use the crane.
Okay.
Yeah.
So at this point in development, what things are you being kept up by at night? Like, what's the thing you're like, oh, we just need to, do this or this better, or we really, I can't sleep because we haven't figured this out yet.
That's right.
Yeah. So what things is totally keeping you up at night at this point? What's the thing that you feel like you still have to solve at this point?
I mean, there's a long list. So,
what's at the top of that right now, for you at least, personally?
Well, this is really all just measured as in terms of time. Like, what is the time risk associated with something?
Right.
The one thing you cannot replace is time. So, and I do have a habit of being optimistic with schedules. If I wasn't optimistic, I wouldn't be doing, the crazy things that I'm doing.
Right.
So I must have, like, I don't know, just pathologically optimistic, I suppose.
Wow, that actually, look at that.
Yeah, it looks like dragon scales.
That is incredible.
That looks cool.
It's actually, like, coming together a lot
It
cleaner.
totally looks like dragon scales.
It really does.
Yeah.
And it's so much tidier and cleaner looking than I thought.
Yeah, I mean, there's a few breaking tiles, but overall it looks cool.
That's incredible. Wow. So, I guess the joints is one of those things that the community has always wanted to know about. You know, I guess the good thing is the flaps will mostly take most of the wind from this area that you see. So I guess you don't really have to cool the inside of the flap joint itself because it's kind of already.
No, actually, unfortunately, we do. I think we have significant. I think again, take a lot of what I'm saying with a grain of salt because I often am wrong. So. So sometimes I'll say something that is wrong. But I'll, I think we have a design error with the non-moving portion of the forward flaps. Okay. Because the reason we have the flaps and the static arrow, basically the unmoving portion of the flaps, are there to do two things: to rebalance the ship, so it doesn't come in engines first, because that's otherwise the center of mass is quite low. Yeah. And it will come in engines first and burn up the engines. Yep. So, first you have to rebalance it so that in a hypersonic regime you're doing like roughly sort of like 60 to 70 degree angle of attack. Yep. Because you're flying a trajectory that minimizes peak heat. But you don't care about total heat load. You just care about minimizing your peak heat.
Because you have a good insulator here, and you're not ablating.
Yes, exactly. So if you have an ablative heat shield like Dragon, technically Dragon is like fairly reusable actually because it's sort of like a brake pad. You can fly it many times. Yeah. Because it's got so much margin. Yeah. But a Pika is literally means phenolic impregnated carbon ablator. Yep. So that's the Dragon heat shield. So Dragon's like, hey, let's have give me a high peak heating, but don't make my total heat load high because what Dragon's trying to optimize for is what is the heat pulse when it's under parachutes and it's been the heat pulse moves through the tile and then reaches the back to where it's bonded to the carbon fiber composite sandwich structure. Yep. And if the heat pulse is if the heat is too high, it will melt the glue, and the heat shield tiles will start forming off, and then they will potentially, damage the parachute. Really? Yeah. Okay. You start having like these things like
flying off.
Potentially, because they're low density, so they're pretty and like it's like, admittedly, it's kind of a corner case, but that's it. That's like the Dragon heat shield tiles are way over thick. Not because of how much of the heat shield will be ablated, but because of the heat pulse that will reach the back of the heat shield that might melt the glue while it's under parachutes. Wow. So
interesting constraint at the end of it all. You know,
yeah. Like, so if you just have a lot of heat suddenly, that's actually better for Dragon. Like high peak, low total heating.
Yep. And so its re-entry profile is totally different too. It can come in steeper as opposed to this.
Dragon wants to kind of like. The lift over drag ratio is low for Dragon. I mean, a lot of people look at it and say it doesn't have any lift, but it does. If you have a gumdrop shaped thing and you have offset center of mass, then you can control it because it has a small lift vector because the gumdrop is like tilting into the wind slightly. Yep. It's quite low. And actually, LOD is a function of Mach number. People will quote an LOD number, but like, okay, what Mach that? Right. And it's usually like some sort of reference Mach number. But like your LOD is complete trash at like Mach 20. It's garbage, nothing basically. Right. So it's like LOD at what Mach number? Anyway, so it's got a very low LOD, but it does have a lift vector. And then because it is symmetric, or more or less symmetric, with little thrusters, you can rotate the capsule as it's coming in and change that lift vector. Yep. And then, so then you have a landing ellipsoid because your accuracy longitudinally is less than your accuracy left to right. Because you're changing lift vector. You say, well, how do you change the point where you land? If you can turn left or right, but how do you change this point? You do a series of S turns. So your S-turn, and depending upon how much you bank during the S-turns, that affects your longitudinal points.
Yes.
And then your lateral points is pretty easy to tune because you have a lift vector going up and
Because
right.
it's not so much, people might think like, oh, you're going up and down. That really doesn't work in the grand scheme of orbital velocities and everything. It's really about just your actual velocity, and where you end up arresting your velocity is where you're going to drop it to the ground, pretty much, more or less.
Yeah, I mean, I think it's just very important for people to appreciate that there's a very gigantic difference between orbit and space.
Right.
It is actually relatively easy to get to space, but it is very hard to get to orbit.
Right.
And then if you say you want to go to orbit and come back,
Yeah.
this is easily 100 times harder than getting to space.
Yeah.
Maybe 1,000. So much harder. That hardly anyone's even, like, you know, only a few countries have been able to do it.
Right.
So, you know, whereas Rotor 10 went to space twice, like 12 years ago? I don't know, was it a while? 15 years ago?
2005, yeah.
Yeah, it was
Yeah.
like 15 years ago.
Yeah.
He went to water space twice.
Yep.
And didn't even need, didn't even scorch the paint.
Right.
So that's like, it's really not very hot if you didn't even burn the paint.
Right. That's true.
Yeah.
That's true.
Whereas this needs like really intense heat shielding, or it's gonna get to, you know, blow up basically.
Yeah. Yeah. It's crazy to see now, honestly. So is there some considerations to make the fix? Can we go out this way, or is it?
Yeah, I mean, just don't let anything drop in your head.
All right. Deal. So there's another barrel section of S20.
I mean, it looks a little garage shop, to be frank, but it's like weirdly like super advanced technology with garage shop.
Well, it is very unique of you guys to basically build the rockets first and then start building a factory around it. You know, like,
Yeah, because the production system is the actual hard thing.
right.
The rocket design is relatively easy compared to the factory. And these tiles are actually made in Florida at a SpaceX factory, which is called the Bakery, in Florida. It's next to Ron John's. Literally.
What's the future for Florida with Starship? Are you gonna get it flying 100%, get it all figured out basically? At least get like orbital version ready, and then start setting up shop in Florida and do like.
Yeah, I think we want to kind of iron out the major issues here, and then we'll certainly be launching Starship from the Cape. We might do more at the Cape, but we'll certainly be launching a Starship from the Cape. And like I said, we make the heat shield tiles, which is like actually quite a big factory to make these heat shield tiles. It's not a small factory. So
Next to Ron John's? I didn't.
well, technically it's next to Ron John's distribution warehouse.
Okay.
Literally, I was like, is that a surf shop? Oh, it's yeah. Or maybe it's like a factory. I don't know, but it's got a Ron John's logo. But the factory, the SpaceX heat shield tile factory is quite big. It's not tiny, because there's a lot of you need to make a lot of these tiles.
And for the most part, I'm surprised at the taper. It looks like they're all still uniform tiles, which obviously is a huge improvement compared to the shuttle. Instead of having 24,000 unique tiles.
As you can see, we're figuring it out.
I'm surprised though, even as the area tapers, it's not. I would thought.
Man, I wonder where Mara's our head of heat shield engineering. It's like I want to text him like, "Yo, man, what's going on?"
It doesn't seem like there's a ton of unique. They mostly look uniform, which obviously will help with.
Yeah, they're not all uniform, but
a lot more in the shuttle. What's your expected? What are you hoping to get for reuse out of these things?
I mean, no meaningful limit. As many as you want.
right back into camera reception for you there for a second. Camera inside of camera.
Yeah, there are different shaped tiles. You can see some of them at the border there are square instead of hexagons.
Yep.
And then because the static arrow is it's still seeing actually a lot of heat. Basically the plasma is hitting this it's hitting the surface, and then it's moving around. It's going to somehow get past it. So you get superheated plasma hitting that thing, then riding up the side of the vehicle, hitting that static arrow. So you actually have a heat concentration there. And then you've got a hinge that's, you have to protect the hinge. This is, if you say like, okay, what's highest probability of failure on re-entry? It's probably the hinge of the flaps.
Okay.
So the rear hinge and the forward hinge of the flaps, because you have to have a rotating thing.
Yes.
But you can't just make everything out of tiles, so you have to have a seal. So you have to have a seal against the tiles. The tiles are ceramic, like a seal against dinner plates that are super hot.
Yeah.
So you can't use rubber.
Right.
So it's going to be a metal seal, and with a tortuous path. What?
Have you thought about back in the day talking about transpirational cooling?
Yes.
Is there a
So
chance
that's
of-
one of the things you could throw in it is transpiration cool the joint.
That would be so cool. I just want to see it bleeding methane, honestly, and just
It'll definitely help.
yeah, because you can kind of purge that joint with a higher pressure gas. You know, as long as it's higher than the ambient air stream or the plasma stream, it will create a thermal barrier.
It's definitely one of the things. If you really want to nail the heating on the hinge, is bleed fuel gas into the thing, because actually even the burning methane is like with air, because air is only like 21% oxygen. So air is like what you say. If you ask me what are you breathing, like they think they're breathing oxygen. You're breathing nitrogen with
Right.
some oxygen.
A little argon.
And some argon and trace gases. So, but essentially, methane with air, which is mostly non-oxygen, doesn't get that hot. So even if it burns, it's not that big of a deal.
Right, because it's already detached from
It's
the
not as
vehicle.
hot as the plasma that's hitting it.
Right.
So, yeah.
Wow.
All right. Well, let's see. I guess the car is okay.
So each tent's kind of a designated, one's like barrel section, one's nose cones, and one's one's just kind of the thrust pucks and stuff, or
Yeah, like I said, it is a constantly evolving thing. So
right.
We've changed what occurs in each production tent and in the high bay and mid bay multiple times. But this certainly currently is focused on the nose.
When you're working on a new high bay too, right?
Yeah, we're building a higher high bay.
Uber high.
It's only a little bit higher than the current one, but it's much wider, and it has two gantry cranes that run full width and depth.
Okay.
So, I mean, it'll feel like a lap of luxury compared to our current high bay.
Like about how tall do you know?
Sorry?
About how tall?
I don't know, probably, it's like 100 meters.
Okay. And this one's like 80 or something?
Yeah, this one's about 80. So it's, the booster height's about 70. Although, it's kind of funny, like, technically, we deleted half a barrel section from the booster, so it's technically 69 point something. Like 69 and a half.
You did that on purpose.
No, it wasn't even me. It was like, the guy's like, hey, we just let me know, we took a half, at 70 meters you have a half barrel, which is a pain in the ass. So they just deleted it, and I was like, cool, that sounds good. I randomly set the length at 70 meters. It's not like anything special about it.
Right.
So, but then I just I don't know. I don't know what's going on. But these certain numbers just seem to be recurring all the time.
Yes.
And so the booster is actually 69 point something. And then it's booster 4 and ship 20. And this is all happenstance.
Right, right. I love
What the
that.
hell is going on? So,
Well, what? Oh yeah, someone had figured out that. Oh, what was it? It was like. Oh, I don't even remember what it was. Something like you were 69,420 like days old or minutes old or something when you went on SNL or something. Like it was like some ridiculous. Yes, it was like the weirdest.
no, I was born 69 days after 420, by the way.
Oh yeah. Come on.
Come on.
This is ridiculous.
It's ridiculous.
That's so funny.
I mean, what the hell?
Oh man. This is insane.
It's like, am I an avatar in someone's video game?
Yes.
Oh, really?
Statistically, yeah.
Okay.
You're probably doing pretty good at the game though. I bet you're like the top ranked player.
Okay. Well, that's something.
So do you have a name for the high bay bar yet?
No, I guess we bounced around different names. We still haven't really made much use of it because it wasn't really critical path, so it's kind of just sat there.
Yeah.
And the elevator, we need an upgraded elevator because we have like this construction elevator.
Right.
So, we don't yet have a name, nor have we used it. But we're making good progress there, installing the Griffin.
Yeah, looks like the grid pin's up. And I like how they're now at, let me try and guess why you're going to put them closer together and not at 90-degree intervals. Is it because you can just change your roll to change whatever axis if you're trying to pitch the vehicle? You really only most of the time probably either doing pitch or yaw. You're likely not doing pitch and yaw when it's coming in for re-entry.
Well, actually, no, we're controlling on 3 axes all the time. Now, technically, you only need 3 fins to control on 3 axes, but
so you can also roll if you need to change your yaw and roll 90 degrees to do pitch.
Well, the control authority you need is much more in pitch than in any of the other axes. So, like, the amount of control authority you need for roll is practically nothing.
Right.
But for pitch, you've got to basically push the booster down. So you're going to push this monster thing into the wind, and it doesn't want to go there.
Yeah.
So the amount of pitch force you need, that's like where you need the most amount of force.
Yep.
So having the 2 pairs of fins like closer together, like more like an X-wing fighter, allows them to contribute more in pitch.
Yep. Which then allows more glide or more of the airframe hitting the sides of the booster.
You care about like how much force do you have relative to how much force you need in a given axis.
Okay.
So you need a lot of force in the pitch axis. So that's where you want to bias your grip fins.
Yep. Yep.
You could arguably say they should be biased even closer together than they are currently.
Yeah.
But this is a reasonable guess.
In between.
Yeah.
Well, because this might end up pitching over more than the Falcon 9. Because the Falcon 9 pitches pretty hard, but it's skinnier, and of course has less control authority with the 90-degree thing. So maybe this could pitch even more and arrest more of its velocity.
It's actually you've got various things that are better, some things that are better, some things that are worse. You can leave it like an airplane, like an empennage, where you've got a rudder.
Yeah.
A rudder and an elevator.
Yeah.
And if your elevator is far away from your center of mass, then the amount of force you need is less.
Yeah.
To change the angle. Like just think of it like a seesaw.
Yeah.
You have a seesaw and or a wrench, and if you have a long wrench, it's easier to turn than a short wrench.
Yep.
So if you have a shorter booster, a short booster is harder to turn than a longer booster. It's depending on where the control surface is relative to your center of mass. Okay. The center of mass is the kind of the where the seesaw, like it's seesawing around that center of mass.
Okay.
And center of pressure. You have 2 things basically. It sounds more complicated than it is. But basically, it's a teeter-totter or seesaw. That's where there's a center of pressure and a center of mass.
Yep.
And it's going to basically just rotate around that.
Yep. Yep.
So if you've got a long stage that where the grid pins are far away from your center of mass, then you need less force to turn it. Yeah. So basically,
Gotcha. That makes sense.
yeah, if it's like a really short stubby thing, it would actually be quite hard to move it. Yeah.
But at least as far as the fineness ratio, this has a lot more potential since it's wider to actually use the atmosphere to slow down before it even has to light its engines. Because like, you know how New Glenn has those strakes on the side, and it looks like they're really planning to almost, fly the thing for a little bit, at a pretty high angle of attack compared to the relative wind stream to really let the atmosphere slow down the vehicle as much as possible. You guys are compared to Falcon 9, is a lot finer or a lot less fine ratio. It seems like you get a lot more lift out of the thing.
Realistically, this is going to come in at something close to terminal velocity.
Right. Oh,
so, yeah.
Yeah.
Because you're trying to get to a precise point. So it's very difficult to do a fast pitch-up maneuver. And also get caught by the tower.
Right.
Like if you've got a very big landing area, then you can do that maybe.
Right.
But if you guys precise landing,
right
you can't do like a sudden pitch up at the end. And then you've got sort of pretty big moments of inertia here. Like big things don't move like small things.
Right.
So like you don't see a super tanker dashing around like a speedboat.
Right.
This is like in a rocket form of a super tanker. So it doesn't move fast. It's like it's like way bigger than a whale. Yeah. So
yeah. Yes, it is.
So it's just not going to move fast.
Right.
Although ironically, liftoff will be weirdly fast.
Yeah.
But yeah, it's
yeah.
Big rotating things always move slower than small rotating things.
Yeah.
Yeah. So it's yeah. Like I said, yeah, there's a lot of potential improvements. I mean, yeah.
Man, oh man, wasn't that an awesome conversation? Now in part 3, we're going to be taking you down to the launch pad, and you're going to be able to see Elon just walking around at work. It's super fascinating. Again, thank you, Elon, for spending so much time hanging out with me. I'm glad that you had fun, and it looks like maybe we'll be able to do this again. You know I'm game for that. And SpaceX, thank you so much for allowing me to share all this awesome stuff with everyone. But I owe a huge thank you to my Patreon supporters for helping make this and everything we do here at Everyday Astronaut possible. If you want to gain access to some exclusive live streams and also our awesome Discord community where we talk about everything spaceflight all the time, head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome web store where you'll find shirts like this, the full flow stage combustion cycle shirt, and the hoodie, and the Aerospike shirt, the rest of the schematics collection, or the future Martian collection. You'll find lots of fun stuff at everydayastronaut.com/shop. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.
Of my daily life. Because when I'm standing at that start line, I'll know this is where it all pays off.
Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome back to Starbase, Texas. This is, of course, where SpaceX is building their Starship vehicles. This is part 1 of 2 parts. In part 1, we're going to take you around the factory, see what's new, see the ships, see the boosters, see Star Factory from the inside for the first time, and just learn a lot along the way. So stay tuned for part 2, where we'll take you out to the launch pad, and we'll also follow up with Elon after the launch and see how it went. So without further ado, let's go on another tour with Elon Musk.
Cool. So yeah, as we were saying, I mean, obviously a lot has changed in the last couple of years. I mean, this is all. In theory, I don't know. I mean,
It's exactly the same.
what once was tense is now a permanent looking factory.
Yeah, it used to be intense, and now it's in a building.
Yeah, yeah.
So we've got this I think pretty good looking rocket factory building that we've almost completed. Completed the exterior. This will enable us to have serialized production of the rocket, especially the ship, which would ultimately be made, long term, probably be making 1,000 a year of the ship. So, you gotta build a city on Mars.
Yeah, that's insane to think about.
Yeah, I mean, we may not build 1,000 a year right here, but I think this is capable of 100 a year.
Really?
Sure.
Wow.
It's only a ship every 3 days.
And
that's nothing.
And well, and it's funny because now, if you think about it, even Falcon 9 these days, you're producing a second stage about every 2 days. And a few years ago, that would have been impossible. No one would have imagined. Yeah, that they're building.
And this year we'll make almost 200 upper stages of Falcon.
That's unbelievable.
Next year, probably over 200.
That's
so.
That's a cadence that people I don't think are, just even, you can't even imagine. You can't even fathom that kind of, output like that. It's just
Falcon
crazy.
9 is actually a heavy lift vehicle, so it's there's roughly 40,000 pounds to orbit.
Yeah.
So, which is in normal rocket language would be a heavy lift.
Yeah.
So, now Starship's going to be able to do 100 tons to orbit with Starship 2, maybe a little more than that.
Mm-hmm.
With Starship 3, at the 9-meter diameter, essentially when the 9-meter diameter is sort of fully stretched out to what ends up being from 120 meters total length to probably 140 or something like that. Then this is like a lot of optimizations, engine improvements, heat shield mass improvements, reducing the amount of propellant needed for landing. Kind of basically do all the things that we've somewhat done with Falcon 9, and you get to a pretty efficient vehicle. I think we'll be able to do over 200 tons to a useful orbit with Starship. So, and that's with full reusability, which is insane. So it's twice the Saturn V with full reusability, and full and rapid reusability. So it's the booster and the ship are coming back to the launch site.
Right. Should we take a look at what's going on in there? So, so as far as we're seeing all this. You're talking about even version 1 maybe be able to do less than 100, but is version 1 really even gonna? I feel like version 1 in my head is just
the point of, and really kind of Starship, we're version 1.67. I don't know.
Right,
It's like we're like many iterations through on version 1.
Yeah.
So.
And it's just a canvas. It's a test experiment still at this phase. It's just I don't think people, they see it and they don't understand that this is all just still a giant test at this stage.
Yeah, one way to look at technology is to look at it as like you're rendering an image in successive levels of detail. So the first layer of the image is very, very blurry and things are out of place, and then with the next pass, it gets a bit more defined, and things kind of shift into place. We do another pass and another pass, and eventually it's something that is refined and actually works.
Right.
But we're in uncharted territory with Starship, so it's not like nobody's ever made a fully reusable orbital rocket.
Right.
And that's really the critical breakthrough necessary for life to become multiplanetary. For us to become a true spacefaring civilization, we have to achieve full and rapid reusability.
Yeah.
So I call it rapidly reusable, reliable rockets.
R squared. Or R.
RRR.
Yeah.
Pirate. Space pirates.
There we go.
So,
and it's the thing is that people need to remember is achieving orbit's been solved. I mean, you guys have been getting to orbit for a long time. reusing it.
Getting to orbit at all was told in the 50s.
Right.
I mean, or, so I mean, I really don't think there's another point in an expendable rocket,
Right.
in my opinion. Or at least I think the math clearly demonstrates that there is no point in an expendable rocket. You have to achieve reusability. We have reusability in cars, we have it in airplanes, we have it in bicycles, horses.
Yeah.
It's bizarre to not have reusability in any other form of transport. Boats. It would be insane to chuck a boat away after a trip.
Right.
But this is how rockets will work for the vast majority of time. In fact, SpaceX is still the only rocket that has any reusability with Falcon 9.
Right.
So with Falcon 9, we bring the boosters back. We refly them frequently. We bring the fairings back. We refly those. It's only the upper stage that is expended.
Right.
Now Falcon 9 does not qualify as rapidly reusable,
Right.
Because most of the time the booster is landing on a ship in the ocean.
Right. So it takes a few days to get it back.
Yeah.
Oh, that's speeding up like crazy. I mean, the cadence out of the cave is unbelievable.
Yeah, we're trying to squeeze every quarter of a knot that we can out of the drone ships.
Yeah.
So
Seems that way.
yeah, we're jacking up the power on the ships, streamlining them, increasing the power on the tugging vessels, so we just haul ass as quickly as possible.
Well, yeah, I think you just had your fastest turnaround just last week. There was it was something like, I don't remember the time, but it was something like 2 days or something. From catching back and then out to catch again. It was just, insane. It used to take so much longer. And those are all those little things that people just aren't necessarily paying attention to. They're continually improving. And yeah,
no, the SpaceX Falcon team is doing an incredible job of achieving fast turnaround reusability, given the architecture.
Yeah.
Now, that's still, however, a couple days to get a booster back, and then at least a few days to refurbish it for flight is still not rapid by aircraft or vehicle. Take cars, boats, planes.
Right.
Doing a trip every 4 days is not. We're not
right.
cut it in a car.
Right.
Or an aircraft.
Right.
With Starship, the booster comes back to the launch site, is caught by the arms. Or, this would be quite spectacular to see. Giant Mechazilla arms catching a rocket in midair, and then those arms put it back on the launch site, so you can have the booster back on the launch mount it's gonna come back and land in 5 or 6 minutes.
Right.
So then we'll probably get it back on the launch site in, well, if you really push it, you probably get it back on the launch site in 10 minutes.
Right.
Or even 5 minutes, and then you can fill it up in half an hour. So you could be ready to go an hour later from the booster standpoint. And then if you've got ships lined up, you can drop another ship on, fill it with propellant, and in theory, you could be launching every couple hours.
Yeah. It's hard to imagine now, but it was hard to imagine where Falcon 9 is today, 10 years ago. No one would have imagined what Falcon 9 is doing now. So I think time will tell that, you can just keep chipping away at all those little improvements. And so do you think you'll actually fly?
Falcon 9 used to have reusability measured in months, then weeks, then days. And then for Falcon 9, the architecture is limited to, you really can't compress it down less than several days.
Right.
When you take the landing out to sea and then the necessary refurbishment of the booster that is required. So with Starship, we'll take it from days to hours.
Wow.
So then the ship has to go around the Earth, and depending upon what orbit it has, it's going to have a ground track that comes back over the launch site.
Right.
So that could take several orbits. So the ship could take several hours, sometimes half a day or something like that to come back.
Reline, yeah.
Yeah. So you'd want to have a lot more ships than boosters.
Yeah.
So if you're really going for max launch rate, you probably want roughly 5 ships for every booster.
Yeah. And that's what you guys are building a pretty massive cadence here of ships and boosters already.
Yeah.
Now, do you think?
Well, I mean, yeah, it's pretty slow compared to what it will be. Very slow. But we're also iterating the design, so each one is a little different from, in some cases, a lot different from the last one.
Yeah. Are any of these what are any of these going to be the V2 yet? Are we starting to get close to some V2 hardware yet, or?
Where luxury meets convenience, that's holiday. Start your journey with Hertz at direct@hertz.co.uk.
Missing deadlines is every marketer's worst nightmare, especially during special events like Christmas, World Cups, Mother's Day, or New Year's. Reducing your creative turnaround time is a simple solution to avoid this. For example, when your marketing or creative department is overloaded or understaffed. So why care about faster turnaround time? It means smoothly meeting tight deadlines, rapidly responding to market shifts, seizing trends, testing and iterating much faster, and thereby staying ahead of your competition. It is a key priority that you should address now.
Yeah. The stretch version is basically V2. Well, I guess it depends on whether we call it V2 or don't call it V2. The slightly stretched version is V2, ugly. So, yeah. So you can see, what we have here is a Starship with, you've seen the heat shield side and the non-heat shield side. Yeah. It's got the what we call the PES dispenser for tossing out the next generation Starlink satellites, the V3 satellites. So those will be very wide diameter, like sort of, I don't know, 7-meter diameter satellites. Yeah. So 22 feet or something like that.
Right.
So
are these actually going to be like? Are we hoping to see after? Let's say this test goes well tomorrow. Do you think the next one's actually going to go for orbit and start deploying testing out trying to deploy Starlink, or are we? Where do you think we're in that whole mix? Like, is that maybe a few more down the road to start actually deploying payloads into orbit?
We'll see how this mission goes. I mean, this year is not about delivering satellites for Starship. It's all about ironing out the design question marks. Mm-hmm. So the major things that remain to be solved for Starship. The single biggest one is what does it take to get through the high heating of reentry? Mm-hmm. So you can see the heat shield that we have there. We have some, let's say unsolved questions on the heat shield. A bunch of which we don't even know that they are questions, and some we're aware of because there have been challenges in the past, like with Space Shuttle. The sort of the hinge area and the hinge gap, and sealing that hinge gap and not having hot gas just go flowing super fast through the
interface there.
Yeah, where the flap hinge is. Yeah. Because if you get hot gas flowing through rapidly, that'll cook anything, including the tiles. So you've got a hot gas seal at the forward and rear flap hinge, and so one of the key questions is, does that seal work? Right. We think it'll work, but it may not work. Then there are some, questions of like how well do the tiles stay on? Right. There's a fundamental challenge here where the tiles are ceramics. They're very brittle. They're like a coffee cup, right? Or a dinner plate. Yeah. So you've got essentially a whole bunch of dinner plates stuck to a steel surface. The steel surface is getting cryogenically cold because of the propellants, so it's shrinking. Yeah. So on ascent, the rocket has shrunk. Yeah. So you can't have the gaps in the tiles be too tight, or they will just shatter against each other. Yeah. The gap will be too tight. Yep. then when it's coming in for landing, the shuttle, you no longer have the cryogenic propellant in the main tanks, and the tiles get very hot.
Yep.
So now they want to expand.
Yeah.
So you've got a contracted inner surface and expanding tiles.
Oh, geez. Yeah.
Right. So and the thing is, like, you can't have a big tile gap because then the plasma will get in there and melt the primary structure behind it.
Exactly.
So, like, what's the right tile gap? And that's going to vary depending upon where you are on the rocket, on the ship. You know, so it's going to be like some parts of the ship have cryogenic propellant, some don't. There's also how well do the tiles attach. If we attach them and we accidentally break one, but it's hard to see, then that could be an issue.
Right.
And we currently think we're probably not resilient to failure to loss of a tile in the hot sections of the ship that are the tank portion. So if
the pressurized area.
Yeah, the pressurized areas,
Yeah.
exactly. So, and since technically the nose will be pressurized too. So if the pressurized areas lose a tile and then you melt that area, that'll cause it to pop.
Right.
So the ship will explode.
Yeah.
So now people have asked, like, why are there some missing tiles in the rear of the
Well,
ship?
like right now, Flight 4, you got I think 3 tiles missing right now. Yeah.
Yeah. So those are in the rear of the ship, which is
At
an
the skirt part,
unpressurized
right?
region.
Yeah.
Yeah. So that's an unpressurized region where we think we can see. Well, you can have a melt through of the unpressurized region, and it will not cause failure of the vehicle.
Yeah.
Like, you might have a little hole there or something.
Right.
But it's not going to pop the vehicle.
Right. So you're literally doing it as like an A/B test, almost of like,
Yeah.
what happens if we're
what
missing
happens
a
if we lose a tile? Now we do have plans for a secondary shield beneath the tiles that is much better than what we have right now. So right now we, and some of this I can't say the details of it because it's like ITAR control is sort of secret. But the current material we use, we think, is not resilient to a tile failure. We have a new design that we think is resilient to a tile failure.
So behind the underlying structure.
Yeah, and essentially it's got ablative. So if you lose the tile, you have to replace the ablative.
Right.
So you'd have to you'd lose out on reusability because of the lost tile and the ablative.
But you have
but at least it's intact.
Yeah.
And
you recover it, you refurbish it, and get it back out on the fleet. That's cool.
And especially for carrying people, which ultimately we expect Starship to carry it maybe 100 people at a time to Mars, and also to the moon.
Yeah.
Then it's going to be super reliable. It's going to have ideally no single point of failure.
Right. So have you given up? A long time ago, you were talking about transpirational cooling or active regen and stuff. Did that just kind of didn't make the trade, or?
The mass trade that we did, I think it's this point, like it's 4 years ago or something like that, maybe 5. It seemed like at that time it would be at least twice as heavy as a ceramic heat shield. Now, since then, the weight of our ceramic heat shield has grown, and then we factor in the secondary shield, that's additional mass.
Right.
So, I don't know, it may not be that big of a difference between actively cooling a heat shield and having ceramic tiles.
Have you seen what Stoke Space out in Washington is working on, where they have it's of course Aerospike's going to come out of my mouth because for some reason Aerospike comes out every time I talk about anything, but it's a Aerospike with the base plug is actually the active regen heat shield. And so it's expander cycle. So as it comes back through the atmosphere, it's actually, heating. They're using hydrogen to actively regenerate, and cool the heat shield. And it just gets dumped out the nozzles basically as it's going, and that actually also gets some of the gas gets vented out to the middle. So you also have like a boundary layer there too gaseous helium or hydrogen in the front, and it's being actively regen. I think it's a really cool concept, and I was really impressed. It made me just think about like regen, active regen in a different way, and I thought that was pretty neat. But I know you guys had talked about the transpirational cooling years ago, so I didn't know if, yeah.
I think it's probably correct that a ceramic heat shield is going to do better than transpiration. There's also the question of like, if you go to Mars and you're coming in at hot and you're coming back to Earth, you come back from Mars to Earth, you're coming in very hot.
Yeah.
It's not clear whether transpiration cooling could succeed there.
Up there.
Yeah.
Here's my wacky, dumb idea of the day is on the inside of the tank, if you had like a thermal camera, you have like a fire hose with cryogenic coolant, just spray if there's a burn through,
sure.
Spray it down from the inside. I don't know. I'll always be happy to throw out the dumb ideas. Especially when you have header tanks there, that are filled with the cryo all pressurized, ready to go. All it's gonna take is one heat shield tile missing potentially, and could have a bad day.
There's a lot of ways to solve the problem.
Yeah.
So what matters is that it is solved.
Yeah.
Even though, there are many ways to achieve full reusability. What matters is that it is achieved.
Yeah, 100%.
And then once you're in the sort of over the hump of full reusability, whether one system is slightly better than the other is a secondary concern.
Right. Yeah, it's tomato at that point.
Yeah.
Should we keep moving along here?
Yeah.
So when with Flight 3, when it broke up, that was mostly just because obviously it couldn't maintain orientation, so it didn't even have a chance of having the heat shield.
You would have noticed that the engines, there was a lot of like fire coming from the engines area. Just that's that's not good.
Yeah.
On re-entry.
Right. Definitely
when
not.
the engines aren't on.
Yeah.
So this is you can see we're just finishing. We're trying to get the shell completed as quickly as possible, but we still have a lot of work to do on the interior of the factory. But this will dramatically improve the production of the rocket.
Yeah.
It's being able to move from one station to another, which is linear adjacent flow.
I don't really know what that means, but
well, the thing that really matters for, people talk about the moving production line of sort of Henry Ford and the automobiles. What actually matters is linear adjacent flow, as opposed to a production line that moves.
So
it's simple.
Okay. Yeah.
Like one step leads to another.
Yeah.
And things move along in a cadence.
Okay. Yeah. Yep. And you don't have to have the physical.
It doesn't matter whether it's a conveyor belt or not.
Got it.
That's a secondary concern.
Got it.
Doesn't matter. It just matters that there's a tempo. So every station has roughly the same amount of work time.
Right.
And things move from one station to the next station, and the specialization of labor at each station.
Yes.
So these are the principles that actually matter.
And that's what you guys kind of solve by doing the tents first, because you could just willy-nilly rearrange things, see how things are actually falling, see what order things are going in.
But the tents were very inefficient once you know what you want to build.
Yes. Yep.
Yeah.
So it was your 5-step thing of don't get too far along in the automation before you.
Yeah, you don't know what you're going to build.
Yep.
It's simple to convey just how much this is. We don't even know what the rocket would look like.
Yeah.
So.
And in some senses, you still don't necessarily know. It's still changing.
At this point, we're confident that this architecture is at least one of the solutions.
Yeah.
That's not to say there couldn't be other solutions like the one you talked about, but that this will work.
Yeah.
It's just a question of ironing out the bugs, and improving the performance of everything from the engines to the avionics to the primary structure, the heat shield, everything.
Yeah.
But it will work.
Yeah.
I think I was mentioning, or I was beginning to say that the most important, the toughest remaining problem is a reusable orbital heat shield.
Mm-hmm.
So nobody's ever made a reusable orbital heat shield. So the space shuttle is the closest.
Yeah.
But that took, I think, something like 9 months and thousands of people to refurbish.
Right.
So it's difficult. One cannot call something that requires so much work to refurbish as truly reusable.
Yeah.
Certainly not rapid.
Yeah.
So for the first time ever, there needs to be a rapidly reusable orbital heat shield, which no one has ever done. So it's a hard problem.
Right.
So that's why I'd say that's the number one biggest remaining problem, and the goal of this flight and really the flights for the rest of this year is get through the high heating, so the heat shield survives.
Yep.
And then the ship is still operational, is able to steer to a specific location and do a landing burn.
Yep.
In the ocean.
Yes.
And then the booster, we wanted to be able to, for this flight, to come back and do a landing burn at a specific location.
Yep.
So
do you know how far out is that going to be? You know,
it's pretty far out. I mean, but I think we're pretty close to that. If we don't solve it on this flight, I think we'll solve it in the next 2 or 3 flights. So just having the booster, do the hot staging, come back, do a boost back, steer correctly, and to a precise location and do a landing burn, and then and essentially do a simulated tower catch. So it's like,
so will the tower actually?
No, it's just
Okay.
The rocket will think it's
Right.
not trying to get caught by the tower.
Right.
At least
I thought
at
it'd be
first.
kind of cool if the tower mimicked it, out here. To
I
make
mean-
sure, because I even wonder, like, how do we know the tower's going to be okay? Like after a launch like that, to be able to.
Well, we operate the tower after the launch, so we can tell if there's any damage.
Yeah.
But if this launch goes perfectly, we'll be able to. We'll have the booster do a boost back and a controlled aero controlled descent to a specific location, initiate a landing burn, and be caught by an imaginary tower.
Yeah. Yeah.
And then the ship, if things go perfectly, which probably won't, it'll get through high heating. It will still be fully operational. It will control itself to a specific location and in the ocean, and then initiate a landing burn, and also pretend it's getting caught by the tower.
Wow.
Now I think I think we've got maybe a 50-50 chance of the heat shield working.
That's decent.
Yeah, like it's a high uncertainty, but like roughly 50-50. But if not on this flight, then in the next 2 or 3 flights, I think we'll solve that.
Yeah. Well, you guys, let's kind of head over here. You guys did make a decent amount of changes to hopefully ensure re-entries better this time. Like you added some new roll thrusters.
Oh yeah.
And a few things like that.
Yeah.
What happened there that the roll thrusters got, because they got clogged, sounds like.
Yeah.
Don't tell me that was the old conversation we had of hot gas thrusters and all that stuff. Or is it which still I'm still confused because
they got ice.
They got
ice in the valves.
Okay. In the valves, not
Well-
necessarily, or in the somewhere along the stream.
They got clogged by ice. We're not sure exactly how.
Yeah.
But if water ice, we'll get into the oxygen side. There's a small amount, since we're the location that we're tapping off the engine is not pure O2. It's got a little bit of water ice.
Why is that?
It's ox-rich gas.
It is actually. So is it coming off the actual?
Yeah.
Like exhaust or the turbine side?
Yeah.
Really?
Yeah.
So wouldn't it have?
It's ox-rich gas, but it's got road fuel.
Yes. Wouldn't it have a little bit of CO2 in it too then? And can that turn into an ice to freeze CO2 at that temperature? Because I think.
Yeah. Well, anyway, it's got stuff that can turn solid at cryogenic temperatures. The thing that's relevant.
Right.
So.
Yeah, ice, whether it be water ice or CO2 ice or whatever.
Ice.
Ice.
Yeah. And it's solid stuff that blocks
things.
Blocks things. So we improved the sort of ice strainers or ice catchers. We improved the valves. And something I think we'll do in the future is move to, for critical valves, series parallel valves. So any one valve failure does not, no matter what happens, does not take out the ability of the ship to orient itself correctly.
So are you avoiding doing like a more of a traditional heat exchanger, like a round Raptor, you know, like I think Merlin probably does that, where it has a heat exchanger to heat up, to be able to provide OLEDs and stuff. Yeah. I'm just curious, I've never heard of an engine using like already combusted to be able to be the OLED gas, you know, like off the pre-burner. That's pretty unusual, I think, at least. I don't know.
Yeah. Well, our rockets are autonomously pressurized. So we're pressurizing the fuel side with gaseous fuel, and the oxide with mostly gaseous oxygen. Now in the case of autonomously pressurized, we have to create the gas. We're not merely warming up a gas. We have to produce the gas.
Oh, interesting. Is that how the shuttle did it too then? Because the shuttle ran on the RS-25s had autogenous pressurization.
On the hydrogen side, yeah. I think that
I guess I don't know if it's on both.
Was it on both? I don't know.
I don't know.
I think it was at least on the hydrogen side. Maybe on both. But when you have autogenous pressurization, you've got to produce the gas, not just heat it up.
Okay.
So there's a lot more mass you've got to come up with.
Yeah, literally.
Yeah. It actually affects our max power especially on the fuel side. So the fuel pump has to work. Well, both pumps have to work harder, but the fuel pump especially is a limiting factor. Like if we turned off autogenous pressurization on the fuel side, we'd actually be able to get more power out of the fuel pump.
Oh yeah, because you're having to drive all that.
Yeah, you've got to gasify. Yeah, you're bleeding mass flow.
Right.
From the,
from the engine.
Yeah, from the engine.
Yeah.
I mean, there's quite a lot of work in taking a cryogenic liquid and heating it up to be a hot gas.
Right.
So phase transition and that big temperature delta. Yeah. So it's actually a lot of work to produce the hot gas from a cryogenic liquid.
That's crazy. So is that what also? Can we kind of step in here and see all the boosters? This is crazy. Is that what also was the blockage of the ox tank on the booster too then? Similar ice buildup blockage, or was it on flight 3 the Raptors were shutting down during boost back burn and had an ice buildup? Is it a similar thing to that?
Sorry, it's hard to hear you.
Yeah. Is that what caused the booster to shut down on flight 3 with the ice buildup? Was it a similar type of thing, like an autogenous pressurization issue that clogged a few of the engines?
Yeah, we didn't have enough pressure to start the engines.
Okay.
So we were low pressure start. The full answer is quite complicated, but because arguably we could have started with lower pressure, or we didn't need to start all the engines. Anyways, this time we expect to have a lot more pressure, and we are able to start at lower pressure, and we don't need to have all the engines fired.
Okay, cool.
Hopefully.
Yeah.
So.
Jeez. This is crazy. Wow. The scale is just almost impossible to imagine.
Got three boosters.
Wow. That's just insane. This looks so cool. Dang.
A lot of engines.
Yeah. It's an insane amount of engines. And right here we're looking at, what, 99 engines for these 3 vehicles? 99 engines.
99 Raptors on a wall.
99 engines and a ship ain't one.
Everyone's ready? Let's shoot!
Nothing beats a Jet2 holiday. So lock in your holiday for next summer now and save £100 per couple with My Jet2. Jet2 Holidays. Package holidays you can trust. Absolute protected. in your battle against Buffet Boy. Weight loss medication from Newman can help.
Yeah. That's absolutely insane. The scale of these things, it's just hard to fathom. Wow. So are you guys trying to move down to 3 grid fins, is that right? From the 4, is that?
It's not a high priority. It's a mass optimization. So you definitely only need 3.
Yeah.
And I think technically you can go with 2, if you're willing to oscillate.
Yeah, like turn for yaw, then roll again for pitch. And...
Yeah, that's definitely, you're asking for a bit of trouble if you just have 2 grid fins.
Right.
But it is technically possible.
Right.
The 3 for sure. But that's a fairly minor optimization.
Right. With the cowbell diverter things, the Olich gas thrusters or whatever, I need to clear something up for myself because I'm getting confused. So cold gas thruster would be like a nitrogen thruster where it's just literally compressed nitrogen goes out of a nozzle.
Cold gas is room temperature gas usually.
Is room temp. And then would we consider that almost like a warm gas thruster?
Yeah, warm gas thruster.
And then like a hot gas would be where it's a reaction probably, like a bipropellant thruster still.
But for both the booster and the ship, you don't really need much control. The attitude control needed is small. So you just can't have a leaky valve or a suck valve.
Yeah. That seems. This is like the third time.
Falcon is all cold gas.
What is?
Falcon is all cold gas. And we've done, I think, 6 starts. So it's this cold gas that has been maintaining propellant settling and attitude control for 12 hours.
Right. Yeah.
So.
And you have a lot of it on tap. So that's. I don't know why that's still a hard one for me to fathom. Even though we've talked, this is the third time
it's got
now.
a lot of hot gas.
Yeah.
Warm gas.
Especially when it's empty. It's all warm gas.
So the delta V needed is tiny. So it's very tiny thrusters are needed. So yeah.
So how much do you feel like after you fly? How much is it like? Oh God, we have to change all of these. Like, is it literally you find something on one and then you're literally like immediately having to make changes on all these things, like everything that's in production.
Yeah.
You're just
there's hundreds of changes that have to take place, not a few.
Yeah.
Hundreds. If you're at a detail level, there might be thousands of changes that happen.
When you get software involved, I'm sure it's
software for sure. I'm just talking hardware. If you just look at the hardware changes across the ship and the booster and the engines, it's thousands of changes between each flight. But many of them are very small. But a very small change could be a big deal.
Imagine how long it'd take a traditional aerospace company that had a rocket they're working on to make 1,000 changes between flights and then fly it 2 months later. I mean, that's what we're doing here. This is you're barely over 2 months from the last flight, and the vehicle's had over 1,000 changes.
Easily over 1,000, several thousand probably. So
that's insane.
Like I said, a bunch of them are little changes, but is it different in a way that could have an effect on the rocket? Yeah. So it's probably several thousand.
And do you feel like for now, are you generally like kind of overbuilding them to just try to get through the point of being able to prove the heat shields, prove all the stuff that eventually you'll work on mass?
We're trying to answer the questions that I mentioned. The biggest question being, what does it take to get through max heating with a reusable heat shield? Then being able to have the booster come back and be caught by the tower, and have the ship also come back and be caught by the tower. Yeah. So those are the 3 very big things that need to happen.
And that's in your mind when you're launching these, including like flight 1, 2, 3. Those are the questions. Like those flights are just to answer those questions.
For reusability.
See, I think people just don't understand that you're not looking at trying to get out there and launch a satellite tomorrow. You're trying to answer questions.
The payload for all the flights this year is data.
Data.
Just to learn things. So it's design refinement to understand what works, what doesn't work.
Yeah.
Some things sometimes work, which can throw you off because it worked once but it doesn't work again because the combination of factors isn't the same.
Yeah.
So you want to have the first things you'll find are like fundamental errors of design, where success was not one of the possible outcomes.
Yep.
Then, in some cases, it's kind of like Russian roulette. Success is sometimes possible.
Yeah.
But once in a while, you blow yourself up.
Yeah. Yeah.
So that's going to require a lot of flights to figure out like the 1 in 10 failure, the 1 in 100 failure, that kind of thing. There'll be a whole bunch of things like that.
Well, kind of even like the SM stuff, when 8 was darn close to landing, 9 was almost a reversion feeling, 10 was better, 11 was worse. Like there's a little bit of a ping pong as things were kind of being tried and tested, and you're still kind of in that phase, even at this scale. I just don't think people are used to that, you know?
Yeah, I mean, a lot of those like early tests were also just about us learning how to work with stainless steel as the primary structural element.
Yeah.
And working with liquid methane and with a full flow station combustion engine as the engine. So a lot of what people saw was that the flight, you know, did it land or not land, but we're just trying to figure out how do we work with steel, and how do we work with a methane as a fuel,
a new engine architecture,
and a totally new engine architecture,
and new flaps, like things that are just
and do the flaps
new and novel.
Yeah. You have to actuate the flaps. You need very powerful actuators for the flaps. For a lot of force, it's like an airplane moving its wings.
Right.
So these are very powerful actuators that are needed.
Yeah, absolutely.
So, you know, and all of the engine to vehicle interactions are very complicated.
Yeah.
So you don't really see those on the test stand. When you're firing the engines on the test stand, you don't get the engine to vehicle interactions. And then you got different engine to vehicle interactions in flight than you do on the ground.
Yeah, 100. Especially when you're changing orientation of a vehicle and different G forces and
Like,
0G. I mean, all the things.
There's no test stand that can test a rocket up to 17,000 miles an hour doing 6 Gs. In every different orientation.
Right. Exactly.
It's not possible.
Yeah.
So
you have to fly it.
Yeah. You do as much as you can on the ground, then you got to fly it. Try to figure things out in simulation, but a lot of things are not going to be included in the simulation, so it'll work in some, but not in reality.
Exactly. It's crazy. Shall we keep moving?
Yeah. Sure.
We're just about to debrief with the crank, and then we'll be able to cross the area.
Jeez. Wow.
You're mid-flow when that Pepsi Max lime hits. A twist of zing, squeeze of sour, a vibe switch in a can. The mood upgrade your afternoon's been waiting for. Because life's too short for flat. Bring out the flavor, bring out the lime. Pepsi Max, thirsty for more.
As you can see, the Raptor is a lot cleaner than it used to be. It looks like there's less stuff, but
yeah, it's already.
Yeah.
But these are still not like we're not the V3 here yet, right?
No.
Is the V3 the same thing as like the LEAD engine? Are those?
Sort of. The LEAD engine was. I think we will do that at some point, but that's really a total tear up.
Really?
Yeah. It looks like the LEAD engine, but it's way more expensive because it still has printed parts. For example.
Yeah.
So, but the next gen Raptor engine needs no heat shield.
Right.
So, and because it's exposed, it has to have cooling. So there's integral cooling circuits throughout all the parts. So it looks very simple on the outside, but it's complicated on the inside.
Like even all throughout the pre-burner and the gas manifolds and everything, it's
all that stuff you see stuck on the side disappears.
Wow. And that's actually that's being worked on now already. That's already.
Yeah, we have a design we have a design that works. It looks like the engine isn't complete.
Well, yeah, you had that render on that presentation. It just
Yeah.
looked like literally like a
Looks
first
like it's
attempt at
missing
mocking
parts.
up. Yeah.
Yeah, but it's actually just the secondary circuits and integral cooling are part of each part. So, so if you have a secondary cooling circuit, you run the secondary cooling circuit or secondary flow circuit through the various parts.
Right.
And we also eliminate a whole bunch of bolted and welded joints. So, especially the bolted joints, you really want to get rid of those.
Yeah. Yeah.
You know, bolts and flanges and seals will help, especially if they're hot. So yeah, the next gen Raptor engine is actually a little difficult to service because there are parts that don't have a flange anymore. It's just welded shut.
Right.
Yeah.
So you're just hoping to be able to get the design up to be so reliable, hopefully that
Yeah.
you just don't need to
If you
service
need
it
to
as
change a
often?
part, you need to literally cut it open.
Wow. So you're probably at this point you might as well just like swap out the whole engine, I assume, and just
No, we cut it open.
yeah.
Yeah. We cut it open. So, but there's, yeah, I mean, there's a massive bolted flange for the hot gas manifold that's transferring hot gas from the fuel recharge to the hot gas from the fuel pump side.
Yeah.
You can see that. It's well, it's hard to point at because up in the air, but the thing that joins the fuel,
yeah, the fuel
turbo pump to the aux turbo pump.
Yeah, the kind of band looking thing.
Yeah, the band looking thing. That has a monster flange at the top and bottom, and we want to get rid of those two.
And that's a whole lot of pressure. Hot.
That's a whole lot of pressure.
Hot pressure.
Yes. Jeez. I mean, you can see there's a lot of flanges here. I mean, this valve is like, this pump is like made of flanges.
Wow.
Flange. And like, these are beast level flanges.
And these are all so there is no like active cooling inside of two like this, or the current version of Raptor like this. There's no
current version does not have. There's no well. There technically is some, but there's not. The current version of Raptor does not have sufficient cooling to be able to resist being in hot gas plasma, like hot plasma.
Yeah.
It's not. Yeah.
That's why you need. That's still why I need the shield here.
Yeah, that's why it's heavily shielded. But next gen, a bunch of the flanges you see here will disappear, and it will have integral cooling and integral secondary flow circuits.
Yeah.
Yeah.
Do you guys look? Is it possible to do?
There's a whole bunch of engines down there. Pretty densely packed.
It's
a lot of thrust.
It's a lot of thrust. It's crazy. It looks like when you go to a Christmas tree store or something.
Yeah.
That's insane.
Each one of these is the most advanced rocket engine ever made.
And they're just being cranked out like it's nothing.
Yeah. Super high pressure, high efficiency, you got a full flow, stage combustion.
All the
It's
goods.
insane, yeah.
Has there ever been any look into, like, I know, with aircraft turbines, you can do, like some kind of cooling on the actual turbine blades. Is there any way to do any kind of cooling on the turbine blades and Raptor?
We've had that discussion many times. We'll probably head back into and see the main factory.
Jeez, I just can't believe how much has changed out here. You have 2 mega bays. I mean, last time I was out here, there's only 1 mega bay, and nothing had doors. Now you have doors. That's a pretty good feature comfort. It's turning into a real factory,
Yeah. Well, this is a real factory that we're here.
Yeah.
So, quite big.
It's hard to keep up with everything out here.
Yeah, so this is we'll finally have a real factory for Starship. Not just making it intense. Yeah, so long term, we want to try to get the thrust of Raptor up to around 330, maybe a little higher, maybe 335 metric tons. So that'll take us to a 10,000 ton thrust at lift off.
That's absolutely absurd.
Sorry?
That's absurd.
Yeah, yeah.
It's like beyond absurd. That's coming up on 3 times the amount of power as the Saturn V.
That'd be roughly 3 times the Saturn V. Yeah.
That's what you
Be
need.
like 22 million pounds of thrust. The Saturn V is 7.5.
Oh my god.
So,
absolutely insane. Well, and I think, you know, there's this kind of feeling of why aren't people doing things like the, you know, the Saturn V being built in the, you know, here in the 60s.
Saturn V is primitive compared to Starship.
Yes, and it's insanely expensive. It wasn't sustainable.
Yeah, and it was expendable. So
yeah,
Starship is I mean, just any rocket that is fully reusable, which no one has achieved, because it is extremely difficult.
Mm-hmm.
Not because they didn't think about reusability.
Right.
So it was just too hard. So, and obviously we haven't achieved that either. You know, we've got a. I'm hopeful that we will achieve it by next year.
Mm-hmm.
So, but at least we have a situation where we have a design where success is one of the possible outcomes.
Yeah.
So, no prior design was success one of the possible outcomes for full reusability.
Well, if you think about it, let's say you guys, for some reason, just were like, okay, screw it. We have to launch 300 metric tons to orbit. You could absolutely, you could expend a rocket if you absolutely had to for some reason.
Yeah, but it's pointless.
It would be pointless. But like you have that capability, like for the first time since the Saturn V.
Well, I mean, generally, if you can do 200 tons reusable, you can do double that expendable.
Right, 400 tons.
Yeah.
Which is insane.
Yeah.
I mean, even to the point of if you had to do, let's say you had to do, you know, HLS or something to try to speed it up or something, to, you know, orbital refueling's not done or something.
No, orbital refueling, I mean, I don't really count checkers before they hatch, but orbital refilling is really just docking with ourselves.
Yeah.
We dock with the space station all the time.
Right.
A space station is way harder to dock with than ourselves.
And but will it be all docking up to a like a depot? Is that kind of the plan? Is there to be an orbital?
It depends on how quickly you want to launch. So if you're going to the moon, I don't think you need a depot. I think you just send a ship up and send tankers immediately.
Yeah.
And your boil off rate will not be too bad.
Okay.
So now for the moon, you'd want to have a dedicated Earth orbit to moon system because you don't need a heat shield.
Right.
Well, you need a heat shield to break, I suppose. Well, probably actually, yeah. The moon's like hotter than it seems because it doesn't have an atmosphere.
Right.
So you can't use the atmosphere to break. So.
But if you have time,
I guess you probably have. But anyway, it's like.
Yeah.
Yeah. For landing on the moon, obviously you don't need flaps, don't need a heat shield, and you need very little thrust.
Right.
But you do need pretty big landing legs.
Right.
So in case one leg lands on a boulder and one lands on a crater, and you don't want to trip over.
Right.
So.
Because that's you know, I think HLS. I don't think a lot of people understand that we're going from a 16-ton lunar lander with the Apollo program to a, you know, I mean, I don't even know how heavy HLS is going to be when it lands. It's going to be at, you know, at least 10 times that massive, at least 10 times that massive, and acres of volume compared to anything that was landed during the Apollo program. And I just think that people aren't necessarily ready for how big Starship will be on the moon. It's basically a habitat when it's on the moon, you know? It's not just a little tiny tent like the Apollo lunar landers.
Yeah. But I think the next step is to go beyond Apollo and have a permanently occupied base on the moon.
Yeah.
Like Moon Base Alpha. That's the next step. So you don't want to just have a few people there for a few hours. You want to have a permanently occupied base.
Right. This factory is huge.
Yeah.
And I guarantee we came back in a year, it'd be just up and running like a normal factory already.
I mean, this will be full with equipment in 3 months.
Jeez. So is there a decent amount of like new stuff that's like, is there hardware coming in here and tools that are coming in here that will unlock like, just mostly production rate or even like new ideas or what's that kind of like?
I mean, you can build any given design in an artisanal way, slowly, with by having a lot of crews come to the same station. But in order to have real production, you've got to move from one station to another, where you have the same amount of work at each station.
Right.
So.
Try Eric Essential Mist to lighten to move effortlessly.
So, in terms of salary, you were thinking...
With Indeed, set salary expectations from the start.
What drives me? I'm not always sure. But when the world's still sleeping, I'm already moving.
This is meant to have a lot of stations. So you'll see a lot of work in progress. And you'll be able to see very clearly, I guess, where the blockages are.
And make changes to it then.
Yeah.
Jeez. It's so funny to think about how, we were only 5 years ago out here when the Mark I and all you had was a tent and Stargate was the biggest thing out here, the little Stargate thing.
Yeah.
And now I almost missed it trying to pull into Stargate today because
it looks like a little hut.
Yeah, it's like dwarfed by absolutely everything else out here already.
Yeah.
It's just crazy. Oh, that feels nice.
Air conditioning.
Holy crap. It just keeps going.
Yeah.
I thought that was the main thing.
Yeah.
Jeez.
So there was more behind that wall.
Yeah. Holy crap. So this is more of a real factory here. This is what the other side will look like.
The other side will look like this. There we're obviously just checking each tile to make sure it's not cracked and it's well seated.
How are you feeling about the way they're actually secured on there, like the mounting point? Is that decent?
We're continuing to iterate on the mounting point. I mean, it has a, 99% of the time it works well. So it's just a question of figuring out what are the 1% that have issues with causes a tile to crack or some other problem.
I always keep thinking one of the big challenges is that you can't access you can't access it from either side really. Like there's not a bolt you can screw on because you have
it's a snap-on.
It has to be a snap-on.
Yeah.
Have you ever seen the furniture mountings where you have two pieces of wood joined together and then you spin a magnet on one end and it spins the nut on? I've always wondered if something like that could be.
I mean, this is basically it snaps on, and you pretty much have to break the tile to pull it off.
Really?
Yeah. That's meant to go on and stay on.
Yeah. Well, and we still see, even on the parts that aren't tapered up, on the main body, we still see some horizontal seams. What's the deal with those seams? I know that was, pretty bad.
No, they don't really matter that much. They're just different sections of the nose cone. So, now, this is somewhat of a debate. You could wait until the whole nose cone is made, and then put the attachment points on at that point. So currently we put the tile attachment points on in sections.
Okay.
So that's why you've got a line.
A horizontal line, okay.
Yeah.
It's probably just a lot harder to, once it's all manufactured, it's just so massive, it'd be hard to put all the attachment points on. Is that kind of the problem?
There's more than one way to skin a cat. This is just a cat getting skinned.
Yeah, yeah.
Yeah, it's not to say that there is not a better way to do it.
Yeah.
There are. The first order of business is to get one way at all that works.
Yep.
Thereafter to optimize.
Yep. Watch your step there.
There's still a lot of work we're gonna do here.
Oh, that's cool looking. Is that the landing tank for?
Yeah, it's a header tank.
Header tank there. That's insane. Jeez. And then are those COPVs propped up against it like that then? Is that what those?
Yeah.
Jeez.
Got a pressurized head attack or something, and the engine's on.
Exactly. Wow. So the like the Pez store that we see on Starship now, do you think that's gonna stick around? Or is there still gonna be like a chomper someday, or is it
Well, for the Starlink satellites, they're pretty flat, so
the chomper makes sense?
there's no point in having a giant fairing for a,
Flat little.
it's a giant flat pancake.
Right. What did the door test go reasonably well on the last one, or because I think you guys aren't doing anything
Had
with
some
it?
issues.
Yeah. It's pretty rudimentary, of course, I assume.
Yeah. But it's well that you've got this sort of really quite sophisticated factory on a sandbar by the Rio Grande.
Yeah. Yeah.
It's like an alien spaceship landed.
Right. Seriously. So are these thrusters here then?
Yeah.
You know what these are?
Little jetpacks. This will take the detailed stuff of the. That might run afoul of some ICAR stuff.
Deal.
Yeah. I mean, I don't know if anyone is going to copy us. That would be. It's a hard thing to copy.
It's come a long way since 3 times.
Yeah, it sure has. I mean, everything's clean in this. There's no mud and dust.
It's better when it has doors on it, yeah.
I mean, everything used to have mud and dust.
Yes.
And birds and things.
There's always some finite mud and dust, but it's much smaller than.
It's a long ways from.
I mean, yeah. Yeah. I mean, the Mark 1 thing, it looked like the junkyard in Tatooine.
Which was charming.
Yeah. There was a lot of dust and mud.
Yeah.
The far side rocket. I mean, the Mark 1 was conceptual, as a concept piece.
Yeah.
I'd say concept art.
Yeah. Absolutely.
Yeah.
So James pointed out that this actually wraps all the way around. All of that is still back there. There's more to it.
That's the dome line.
Jeez. That's the dome line.
And the coils, that's the starter lines over there.
That's crazy.
Yeah, so we do have an existing factory that's wrapped around the one you just saw. That's where we make the ship and the booster.
So now we'll open up and it'll start
Yeah.
serpentining it basically through there.
Yeah, that we'll take down that wall there. That is, once we have the doors on the other side, we'll take down that wall, and then you'll just have the factory will just kind of go as far as the eye can see.
It's so much bigger than I thought. From the road, it looks big from the road, but it's insane.
Yeah.
It's ridiculous.
And obviously, the sections get gradually bigger as you go south.
Right.
So that's why things start off sort of short and then get fuller as you go along.
even the roof line does that,
Yeah.
right?
It's going to get bigger if the pieces get bigger.
That's absolutely crazy. Are you guys still using I remember back in the day there's a lot of Tesla motors being used.
Actually, you said that way.
Not that way. Okay.
So
there's a lot of Tesla motors being used, for the fins and all that kind of stuff, and maybe even the grid fins had literally a Model S motor or something. Are you still kind of using some Tesla parts like that?
Yeah, we just use the Tesla drive units to actuate the grid fins.
And the big flaps still too, on the ship?
Yes. Sorry, yes. Essentially, sorry, I was thinking about something else. Yeah, hey, we use we're trying not to use hydraulics. It's all electric actuation.
Yeah.
So the engine's also gimbaled electrically.
Yep. So you're really moving away from hydraulics wherever possible. Really.
Yeah, I think there's actually no hydraulics in the vehicle. If there's hydraulics, some very tiny little part.
Huh.
But I think there's none.
That's wild, actually. I can't even think of another.
There's pneumatics.
Right. A lot. For all the valves and everything, obviously.
Yeah.
That's crazy. Jeez. It's surreal compared to what it was
Yeah,
just a little bit ago. Wow. It just keeps going and going. That is crazy.
Yeah. From one little tent.
Yeah. This is starting to make Hawthorne look tiny, and Hawthorne's a big, well,
Hawthorne's actually a whole campus.
Absolutely crazy.
That's Meme Street.
Meme Street?
Yeah.
Is that what it says now?
That's what it's called.
All right, I think we're jumping in a different car here.
But if you look at the street sign,
We got Meme Street.
yeah, it's literally called Meme Street. That is its official name. It used to be called Weems, and we changed it from Weems to Memes.
The important things. I love it. Holy crap, was that incredible or what? Huge thank you to especially Elon Musk for showing us around and following up and just teaching us so much about what's going on and showing us the inside. Huge thanks. Amazing. And I also owe a huge thank you to our supporters, especially those over on Patreon. If you want to support the work we do here, head on over to patreon.com/everydayastronaut. And now is a great time to be a supporter because we already have part 2 up for review. So again, patreon.com/everydayastronaut to catch part 2 right now. But even if you're not a supporter, fear not. Part 2 is coming out once reviews are done, so be sure you're subscribed so you don't miss out. And while you're waiting, a good free way to support the channel is to just watch some recent videos that you might have missed, like other tours of companies or deep dives on alternate launch concepts. So click around, watch a few. It truly helps the channel out. And while you're online, be sure and check out our awesome merch store for shirts like this, our new orbital shirt, and lots of other incredible things over at everydayastronaut.com/shop. Thanks everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.
Everyone's ready? Let's shoot!
Try Airwick Essential Mist, now infused with 2 times more essential oils.
And here we go. Chamber pressure looks good. Another 43 uncles to go. Indeed. We rise together, back to the moon and beyond. This is nothing to do with players, right? We don't need any more of these.
All right, folks, you know the drill. Let me know over in the chat if you can hear and see me. John Galloway with NSF here today on a Sunday, and it's time for another NSF Live. We did a survey, actually. We did a little bit of poll with the viewers, and we asked what sort of guests y'all like to see on the shows, and the winner by far was rocket company CEOs. So we sent out some messages, and we've got a rocket company person here for you today to talk about Stoke Space. Dr. Andy Lapsa, geez, How is it going?
Good. How are you? It's great to be here. Thank you.
I'm good. I'm talking at like 125% of rated speed, and I'm going to stumble over things a little bit there. But thank you so much for taking time out of your weekend here to chat with us.
Well, it's my pleasure. Thanks for having me.
All right. So housekeeping real quick. Y'all know the drill with our NSF Lives. This is a live chat. We're going to have a conversation about all the different cool stuff that Stoke is doing. If you got questions for us over the course of this show, tag us in chat at NASA Spaceflight. If they're good questions and they're topical about the things that we're covering and stuff like that, we will grab them and we'll see if we can pass some of those along to the guy who should know here, Andy. So one more thing, if we see things like super chats and stuff like that come in when we have a special guest, we spend all of our time with the special guest. So I won't be reading those out, although we do appreciate your support so we can keep doing things like this. So Andy, we're going to hop right into the show here. People can hear us and stuff like that, it looks like. How do you wake up one morning and you're like, well, there's rocket companies out there, but I need a different type of rocket company. How do you make that decision?
I would say first it was an evolution. It wasn't one morning I wake up and decide to start the company. But look, I think when you look at the economics of launch, the economics of full rapid reusability are so powerful that there's really no other future end state, right? So to me, that is inevitable. That will happen, full and rapid reusable rockets. And if you look out on the landscape, number one, there's only one other company pursuing that. It's called SpaceX. And when you look at it from a technical perspective, it's my belief that you really have to design that from day one into the vehicle. You can't kind of back your way into it later. And so, when I was kind of thinking about what I wanted to do next, I looked out on the landscape and it was, honestly really surprising to me that nobody else was pursuing it. And I think that there absolutely need to be more than one player to have a healthy economy for space mobility. And so there's got to be somebody else other than SpaceX doing this, and it wasn't out there yet. So here we are.
Excellent. So that's what you did. I mean, you didn't come straight out of getting a doctorate in aerospace technology into creating a company. You did a couple other things first, but you sort of got to the point where you said, something, nobody's doing the exact stuff that I think should be done, right? And so you went off to found Stoke Space. Is that sort of how it went? Instead of taking these ideas somewhere else, like what you're doing so radically different, you decided to do it right. We need to be in control of how it's working.
Yeah, I suppose. I spent about 10 years at Blue Origin first doing engine development and, really cut my teeth on that. In fact, worked BE4 for a long time. And so I'm super excited for today to see them fly finally. And I think I learned a lot. I think the market has changed a lot in those 10 years. So this is, call it 2009 to the next 10 years or so. And what you saw happen was, first of all, commercially viable business cases actually started to emerge, especially as SpaceX started to improve the cost economics and availability of launch. So you finally had, viable business cases happening. You've got this really exciting new, talent pool within our industry that really hasn't existed before, where you have people, something like me, who have kind of gone through this process of blank page all the way through flight, maybe multiple times by now, and really done so with pretty small teams. That talent pool didn't exist in 2010, right? But it exists now. And then the third kind of ingredient that really, gave me conviction that now is the time for commercial space to really take off was the technical tool sets that we have. We can do so many powerful things with modern computing and analysis tools, and so that you can pull this stuff off with a very small team on a relative basis. So you have those three kind of ingredients coming together for the first time ever. It makes it really, really exciting in our industry. I think that's why you're seeing so much activity. And I think now is the time to knock that last domino over for the industry and get after vehicles that come and go to space, every day.
I like it. What you said is something that we don't think about very often. Like, you used to be these big monolithic organizations that needed to develop these things, right? And with the tool set, sort of the way that technology has increased, then we don't have to go out. We can simulate so much stuff. We can test things before we really dig into it. And the ability to dig into it, like after we've made technology, we've made the hardware, we go out there and we do the engine tests. You're right that we used to not really have that that ability to work on this sort of scale. And now smaller organizations, I guess, can be so empowered to go out there and test things. So you've got so many things like this, right? You didn't just say, okay, here's what a rocket should look like, and now I'm going to make another rocket that looks like a rocket should look like, and it's going to have a little pointy end up here, and it's going to have a little nozzle that fire comes out of. Like your rocket is similar, because rockets like rocket shapes, but it's got some different pieces. Let's start talking through some of the technical differences about what Stoke is working on and how it's different than what anybody else is doing right now. Where do you want to start with that? I mean,
yeah, that's a big question. I think maybe start at the very beginning, right? 100% reusable rockets. That's the inevitable end state. So that's my conclusion number one. Conclusion number two is you can't back your way into it and figure it out later. It has to be designed in from day one. And
right.
so once you have those two pieces, the third piece is, okay, what's the part that the industry doesn't have a playbook for yet? And that part is the reusable second stage, upper stage. And so that's where we started to think is, and it was important for us. First of all, my co-founder Tom and I basically left our last job with that much in hand.
Right.
We didn't really have any solutions. So the first piece of this was, can we take that question and turn it into an engineering problem and not a science problem? It was really, really important for me to have my own conviction that this is something that is, I guess, responsible to take somebody else's money, namely, venture capital or whatever, and go
right.
and put something together that was executable. Okay, so we're trying to solve this reusable upper stage problem. Obviously, the thing has to go and deliver things to orbit. That takes some amount of high performance in order to be able to go and perform that function. But then to get it back, it's not enough to just bring it back. It has to, if it's going to be rapidly reusable, it's got to land and fly as fast as possible. Our mental model is we want to turn this thing around in a day. So if you
right.
do that, you have to think about at least as hard about what you cannot do as you think about what you can do in those 24 hours. And I guarantee you, if it's gonna turn around in 24 hours, you're gonna be pretty damn busy restacking the vehicle, reintegrating payload, getting it back on the pad, refueling, and flying, right? So there's absolutely no time for inspections between flights. There's no time for refurbishment for sure. And
right.
so this thing has to be bulletproof, right? And this is the way we operate. I mean, it sounds kind of radical maybe, but this is how we operate aircraft every day. They're not inspecting the damn thing between flights.
Yeah, Vistaprint prints business cards, but we also print these, and those, and engrave that. We print your brand on everything, so customers can notice you, remember you, and fall in love with you. If you need it, we print it at vistaprint.co.uk. Nothing beats a Jet2 Villas holiday. So, book now and get your flights, car hire, and villa all included. Jet2 Villas.
More of a walk around, right? They're not going and opening every hatch and stuff like that.
Pre-flight check. Yep. And so
Yep.
So we do that. We do that a lot with built-in bit checks and software and obviously visuals, and you see that happening on other vehicles that fly as well. But anyway, so that's what you have to spend your time on. That's it, right?
Right.
And so there's no inspections, there's no refurbishment, and because of that, you need some re-entry method that's just bulletproof. And when we think about the traditional ways to bring something back from orbit, there's really two. One of them is the ablative heat shields that burn away between, on the way in, and that's a perfectly robust system, but it's just not reusable. So that's out. And then the second thing is, kind of the ceramic tile solution that Shuttle used, X-37 uses, Starship is using. And man, that's a technical challenge right there, in my opinion, on this rapid reuse problem. There's two challenges. One is, first of all, there's thousands and thousands of tiles on Starship and Shuttle and whatnot, and every one of them has to stay bonded. So that's challenge number one. And challenge number two is please don't crack them, right? Don't crack them from things like micrometeorites, bird strikes on reentry, even mundane things. If you think about long service life, you're going to have, technicians bumping them, dropping wrenches, whatever, right? And what do you do then?
The engines are going to ignite some of sort, like.
Yeah, right, exactly. You're going to have debris. So what do you do then? I don't know. Are you happy going without inspecting? And my position is you have to be happy to go without inspecting, right? You have to, because these things will happen. It's inevitable. So that's the question. And us being engines people, we cool the inside of rocket engines with this really very powerful cooling strategy called regenerative cooling, right? Where you're pumping propellant through coolant channels in the skin of the engine. And we cool engines regularly at, the heat, the thermal environment in there is about 10 times higher than the thermal environment from reentry. And so, when you come from that world, the thermal challenge is not actually that hard. And so we thought, wow, this is a very powerful mechanism. Can we use that and extend it to the entire vehicle and do so in a way that's mass efficient enough and I guess performant enough from an ISP perspective? And so, so that's the evolution in the thought process. Now the question is, all right, how do you do that? Do you cool, bring it back capsule style and cool the base of the vehicle? Do you bring it back in the belly flop strategy, Starship and Shuttle style? And for a number of reasons, we settled on the capsule base first reentry strategy. One of those reasons is cryofluid management coming back in. The belly flop has a cryofluid management challenge that, Starship, we saw them work through that. It was very impressive. But still, they had to do that. But there's all the slosh that gets introduced from that maneuver. Yeah. From a payload perspective, we're able to design a thing where all of the loads are in the axial direction, whether it's on launch or reentry. And so from payloads, you can design your payloads to take the loads in that direction. You can also design the vehicle to take the loads in that direction, so you get some efficiency there. And so we liked that. And then from a surface area perspective, you have to cool maybe a smaller surface area than you do if you bring it back belly flop first. Okay, so now we're there.
Right?
Yeah.
Like real quick, there's a trade-off, because if you use the broad side of the barn, right, you can get more drag to help slow you down more quickly, but you have a much larger surface that you both have to deal with cooling, and you also have to deal with inspecting or making sure it's good to go for the next flight. So if you're just protecting the bottom of the vehicle instead of the entire side of the vehicle, not only have you diminished or I guess optimized the surface area you have to protect, you've also got a smaller surface area that you need to make sure is good to go for the next flight, right?
That's right. Yeah, 100%.
Cool. All right, folks, real quick, there's so many questions that are coming in as well, and I will try to get to some of the questions, but Andy is mentioning so many different things here, like when he just talked about the structure, and then you have the vertical integrations versus the horizontal, and the loads are going this way so you can be more efficient because you don't need to deal with it. Like, there's so many things that he says at once in a sentence, and then 15 questions come like this. We will try to dive into some of these things, but right now we're talking a little bit high level about why, like, how did you get here? How did you think, let's design this vehicle? Not trying to shoehorn in like, well, we have a second stage, what if we put a heat shield on it, right? We want something that comes back from space. We can't do it traditional rocket style, which is throw pieces off as you go to become more efficient, right? You need to bring most of your pieces back, except for the fuel you throw out the back, right? But we're sort of talking through this right now. And Andy, you say so many things, and I'm like, that could be a 30-minute discussion, and that could be a 30-minute discussion.
Well, I would say a lot of thought did go into it. There's one more step, and that is, okay, now we've got a capsule coming in base first. It's regeneratively cooled to cool it. The last question is, how in the world do you bury a high-performance upper stage engine into a heat shield?
It had
and
that
so,
glowing purple.
yeah, exactly. And so that's kind of the last question that we had to ask for ourselves. Went through many, many different interesting designs to get to where we are, and I think most of the audience probably knows it's a set of discretized thrusters fed by a single set of turbo machinery arranged outside the perimeter of the vehicle, and makes use to some extent of the aerospike effect, but certainly it's not like we set out and said we're going to design an aerospike. It's very different for various reasons. It's very different from a traditional aerospike.
Yeah. Can we get a photo? There we go. There's a photo of the bottom. So, is this one engine or is this multiple engines? Does it really, like, what is the differential between how you define how many engines this is?
I don't know the answer to that question, actually, but I do know, I consider it one engine. It's certainly one engine program. It's a single set of turbo machinery, so there's one turbo pump for the fuel, there's one turbo pump for the oxygen, and it feeds a common distribution circuit, which is actually the heat shield. And and from there it feeds all of the discretized thrusters around the perimeter. In this picture, we have 15 of them installed instead of a full set of 30.
There's just like blinds in between each one, and there should be double that many in a normal loadout, I guess.
Right.
All right.
That's right.
So does everybody understand sort of what we're talking about here, right? Those rocket engines look funny because it's not one bell on the bottom of the rocket, or 5 bells, 7 bells, 9 bells, right, that are down at the very bottom. You can see the curve. I guess that's the tank there, right? Does this one have the heat shield on it?
The curve on the bottom is that what you're referring to? It was taken out of
this image
fire.
here.
Yeah, that is the heat shield. Yep.
That is the heat shield.
That's the
Okay.
heat shield.
So you don't have the engine in the middle, and then you have to deal with the fact that all your engine hardware or the nozzle or the thrust has to get through the heat shield somehow. What Stoke has done is they put the engines around the outside, and the center is just the heat shield. But what Andy just said, there's one set of turbo machineries and one sort of distribution. That means every little flame you have there doesn't have its own discrete turbo pump to pull the fuel out of the tanks and stuff it into the engine, or I guess here through the heat shield and then into the engine, right? In one distribution channel, like it's all going through one system. So that's sort of where you get into how many engines is this. You couldn't take one of these nozzles off the side and be like, here is an engine, it works on its own. Like they need that single turbo machinery and distribution system to feed the combustion chamber. So one set of fuel and distribution, multiple combustion chambers, you're gonna have 30 around the base of it. Look at that. And when I saw that at first, I was like, what is this company doing? Like, that's not what a rocket engine is supposed to look like.
Yeah, it's
you
weird.
Get that. You don't have to penetrate the heat shield. You have it around the outside, so you can have that single, or I guess the single piece heat shield. I guess not technically a single piece, but you know what I mean. The engines aren't poking through it; they're around the outside. How do you steer though? Like a normal rocket engine, it needs to waggle. TPC checks.
Well,
Those
so-
are super
yeah,
important.
this is-
to count.
This is great. That was one of the next questions, right? Not only do you have to bury the engine into the heat shield somehow, but you also have to steer the rocket.
Yeah.
And similar to ceramic tiles, if you have a gimbaled solution where you're swinging the engine around in order to steer the rocket, somewhere in there, by necessity, will be a hot gas dynamic seal. It has to be, right? And similar to ceramic tiles, Tom and I kind of looked at each other. We're working through all kinds of different ways we could package such a seal. And we're just like, dude, we will never trust that thing. No way.
Right.
Maybe it'll work the first time, but not on flight 50 or 100 or whatever. And so that also contributed to the final layout here, where the thrusters are on the outboard side. They don't swing, they don't move. And the way we control the vehicle is through what's called differential throttle, where we'll throttle up one side of the vehicle or the engine and throttle down the other side in order to give a pitching moment on the vehicle.
Gotcha.
Yep, and so
let
all
me
of those
unpack-
thrusters are all they have individual throttle control ability. You actually have throttle control in 2 different places. One's with the pumps. So the bulk engine thrust can be throttled, and then the relative thrust from one side to the other can be managed by the individual thrusters.
Right, Essential Mist will lighten the mood effortlessly.
I'm not always sure, but when the world's still sleeping, I'm already moving.
So let me unpack what Andy just said here, right? You have the engine, and if the engine needs to drive the rocket by vectoring, right, by waggling back and forth using like a thrust vector control, you have moving parts, and so that's all good and well when the rocket's going up and all the force, the aerodynamic forces are on the front of the rocket. That's why you have the pointy end at the top of the rocket, right? Behind it, where you have the engine and the boat tail, you really don't have to worry about air trying to. You should probably have to worry about it a little bit, but force its way in between the engine bell and the rest of the boat tail and the machinery and getting into your cavities where all this stuff is protected, right? But then turn the rocket around and have it come flying tail first. Now, when it's re-entering, all of a sudden the forces are reversed. I guess maybe not technically reversed, the rocket direction is reversed. And so the forces are hitting the bottom of the rocket and not the pointy end of the rocket. And so how do you keep, with these little waggly machineries that have to have seals around them, how do you keep that from impinging up past the seal and getting into your machinery, right? That's what Andy was sort of saying there about the seals. And you've solved that by removing the fact, or removing the need for the engines to. I like this waggling motion, by the way. Like everybody knows what I mean. The engines.
Yeah, the best part is no part.
Yeah.
The best part is no part. So design it out. That was the answer.
So how do you steer the rocket then, right? So your engine nozzles are fixed, and you can't just waggle it in one direction. So you get a little bit of a lever arm, so you get some torque, so you can turn the rocket one way or the other, right? Pitch and yaw the rocket.
Yep.
So how do you steer the rocket? That's where the differential thrust comes in. And so Andy just said two things. The turbo machinery, remember we said the turbo machinery is all one set and it feeds all the engines. So your gross throttle, like for all of the engines, you can change the flow through that turbo machinery that's feeding the engines, and that'll change all of the engines up and down. And then if you want the rocket to lean one way, well, your engine can't waggle, so what do? You put less thrust on one side. I'm going to say more thrust on the other side, but maybe it's just less thrust on one side and then it leans in that direction, right? And so there you can control the thrust of every one of the independent engines. Is that with there's like a valve or a pintle or something like that? How do y'all lessen the output on one nozzle, one combustion chamber?
Yeah, they each have their own throttle system, which is, let's call it a valve. Yeah.
Gotcha. A valve, all right.
It's kind of integrated into the head end of the chamber there.
Gotcha. So you have your entire thrust with the machinery as a whole that feeds all the engine, which is you're coming in for a landing and you need to throttle down so you land and you don't take back off again. If anybody's ever done that on the moon in Kerbal. And if you need to steer the rocket, you turn down the engines on one side by sort of limiting the flow through them. That gives you less force on one side, the same force on the other side. So you have a torque, you have a differential there, and the rocket starts to turn. Is that what it works? Like, is it stays constant on one side and lessens on the other side?
There's different strategies you can use, but and typically, it depends where we are in the mission also. You know, if you're operating the engine 100%, then yes, and you typically don't need as much control authority at that point. If you're operating the engine at 50%, 40% power or whatever, you do have the freedom to go up or down, you know, so we use a combined strategy, let's say that.
Gotcha, a combined strategy. And Andy, if I start to like get too much into the weeds, just be like, dude, seriously? I'm super interested in how this works, because you say, oh, there's two strategies. Well, there's two theoretical strategies, but you're the company that's sort of making this rocket science into rocket engineering, right? You're making hardware that does this stuff.
Yeah, you can see it happen. You know, if we have the, I don't know if there's Hopper video on here, but you can kind of watch the strategy go up. You know, we took off from the ground pad or whatever you want to call it, concrete slab.
Yeah.
And then you'll watch the vehicle kick over, you know, at a very prescribed point in flight, and then come back down. But that's it, right?
First,
you described it better than I can.
I say simple test, right? But there it goes.
Yeah,
by the way, that's not tethered, is it?
No, it's not tethered. That was a exciting point of discussion for us internally. Do we tether or do we not tether? And ultimately decided, well, we can talk a whole lot more. There's a lot that went into this test, and there's a lot that, I guess, went into determining the flight profile there too. But you can see the differential throttle kick in as the vehicle goes up. I don't know how high, 10, 15 feet it was before it kicks over there.
And it does kick over, like when it kicked over, you saw it move.
yeah, the idea was go up. We didn't want to land exactly on the spot where we took off.
Yep.
So kick over and see if we can land it a little bit further away. There
Just
you
to
go.
demonstrate some translational control authority, because it's all good if you can go up and down, but the important thing is, do we have the authority to start a move and then recover control, like stabilize while moving, and then stop a move and then come back down again? You think, oh, it's super simple. It just took off and it landed again. It went over a couple feet. Think about the discrete steps that have to happen in order for that to land on the ground in one piece. I'm going to come out there and do a FOD walk drill, by the way. That's
Well, I will say for things like this, you'll think you get everything, and then, you know, even through the course of the day, if stuff's blowing, it's just coming off of a concrete slab like that, right? So, yeah, all kinds of stuff.
So no kidding. You solved a couple of the different problems there. You want this thing to come all the way back from space. It's not something that's been designed or in wide use or something. You know, you have a capsule, and if a capsule comes back, it has a heat shield on the bottom of it, and the capsule slows down by the aerodynamic forces on the heat shield, and then parachutes, right? But you want to land with engines, you have to have those engines pointing down. So all of the things we've just talked about are probably like a very small 25-minute slice of the things that you had to think about in order to get this far. And we haven't talked about 1/10 of the things you had to think about for this vehicle. So let's move on to other things. We didn't unpack the regenerative cooling that much. You talked a little bit about you have tiles or you have this regenerative cooling. There's a different way there's multiple different ways you could do that. You could have a coolant, you could have water, it could come out and be thrown overboard. And what did y'all decide to do with the regenerative cooling to support your idea that you wanted this thing to be rapidly reusable all the way to space, all the way back down again?
Well, I think the first thing is you gotta do all those things we just said, but it still has to perform its function, which is to deliver payload to orbit. And and because of that, it has to be very mass efficient. Now we can talk about sizing the vehicle and all of those things, but the bottom line is we wanted to build something that's complementary to Starship, right? The way I think is you have to hope and expect that Starship will be successful, and when it is, you know, that's a very exciting day for all of us, and we want that to be good for us, and I think it will be good for us. But that means we also have to be competitive in the Starship world and be also different, right? We have to offer something unique, and I think the medium class rocket does that, provided that we can match them on price and cost, and kind of provide something unique in terms of availability or accessibility or size, direct to final orbit, et cetera, et cetera. Okay, so the point of that is, go ahead.
Just real quick, the analogy on that, because I hear this all the time, and we try to help educate people. Oh, once Starship is flying, we won't need any other rockets, right? I don't want a cargo ship delivering my Amazon packages to my front door. I don't want an 18-wheeler trying to go through the turning circle, right? I don't need these huge monolithic things that are taking huge amounts this distance. We need sort of, I don't know if last mile is really the right way to say it, but that's what you're talking about here. It's not that Starship's going to do every single thing and we don't need any other rockets. We may still need final mile, for the lack of a better analogy, right?
Yeah.
I guess it's not really final mile. It's not.
You can think about it final mile. You can think about it as express shipping. You can think about it any way you want. I think, you know, very fundamentally, economically, you don't want a monopoly either, right? You don't, right? In order to have a healthy economy, I don't. Yeah, you don't. And so, you know, that's especially true as companies start to go into other, you know, verticals. You want healthy competition in each of the verticals. And so if you have one company controlling access to space and you have one company controlling telecom, it's going to be very hard for any other company to enter that space because they're at a fundamental disadvantage without owning mobility, right? And so, you know, I think even SpaceX wants, they may not admit it, but I think anybody who wants a healthy economy in space in the long term, there needs to be some level of competition, right? So that's part of it. And what I was going to say earlier is, if you're building a medium class rocket, you don't have the economies of scale at your advantage that something like Starship does for the actual mission, delivering the thing to space, right? So you're working on a smaller scale, and the whole thing has to be mass efficient enough to do it. And so that feeds into our technical design as well.
Everyone's ready? Let's shoot.
Try Airwick Essential Mist, now infused with 2 times more essential oils. Check out this 3-pack of boys' school shirts from £9. All these Kickers durable patent leather school shoes from £50. Get up to 12 months to pay on your school shop with Very Pay and pay no interest. Very, let's make it sparkle.
Right. And we were getting into the regenerative heat shield being mass efficient. You don't want to carry things that you don't have to, right? That's the huge thing about the rocket equation, rocket science, like figuring out exactly how this math works. If you carry things on your rocket that aren't fuel, aren't payload, that means that you have less ability to carry fuel and payload. So you get into the materials your rocket's made out of. You get into things like, well, yeah, we could cool that heat shield with water or something, right? Well, what else is the water going to be used for? Is it going to be dead weight until we use it for the heat shield? And that's where you got into this idea of using your propellant to cool the heat shield, right?
Yeah. Yeah, water is an extremely efficient coolant, but you're right. If you use water as a coolant circuit, you need an entirely separate system. You need water tanks, you need the water itself, you need water pumps, you need all of those things, and they are exactly what you said. They are dead weight. They're pound for pound. They are dead weight for the entire rest of the mission. Hydrogen is part of what led us to use hydrogen in the upper stage. Hydrogen is extremely efficient coolant. Also, it's about depends on where you are in the temperature range, but between 5 and 7 times better coolant than really any other propellant that we use in rocketry for cooling. And so it's extremely efficient there. It also gives you very high specific impulse. And so anytime you're bringing back the second stage, you need to build that elbow room into your design somehow in order to pay the reuse penalty, basically, right? So you can't pay the reuse penalty if you have no margin to begin with. So where do you get that margin from? Hydrogen gives it to us. And then it also creates a very efficient means for cooling on reentry. And we're able to basically use all of the systems that we already have on board to do the ascent part. We just use them again for the reentry part.
Right. And so, like, to explain what this means, like, the hydrogen is actually not only used as the rocket fuel, right? But you're also flowing that hydrogen. I mean, sometimes you use that propellant itself to cool the engine. You're flowing the hydrogen through the engine bell, or sorry, through the heat shield. Of course you're flowing
through the heat shield, yeah. Yeah, if you find that picture, if you found the picture of Hopper where you're looking up at the heat shield, it's gonna see if you can find that, pull it up. But
we get there? Yeah.
Yeah, there you go. So you see there's like white stuff on the bottom of the heat shield. That's frost. All right, so we are flowing liquid hydrogen through that heat shield. It comes in the center of the circle, basically, and flows radially outward.
Yeah.
And it's cold, right? So that is frost on the heat shield. The whole thing operates at very low temperature, and then comes down, and there's obviously. What I was going to say. Oh, and so this is operating in the day, and one of the things, if you're familiar with hydrogen fires, you really can't see them in daylight.
Clear.
Beautiful at nighttime, but you can't see them in daylight. But there is a raging fire happening right under that heat shield, including where the ice is, and that's kind of cool. You saw the picture earlier of the engine on the test stand, where you could see, it was a night picture, you could see all the fire underneath. Basically looking at the same thing here, you just can't see it. So even though there's fire right there, yep, there you go. Even though there's fire right there, it's it's frost. Yep.
So you take the hydrogen, you flow it through the heat shield. That helps keep the heat shield cool. You flow it through the engine. That helps keep the engine cool. It flows through pumps. That helps the pumps, like all the different things that it does. But one of the critical things here is you're not carrying something else. It's not heat tiles you're going to have to inspect and replace, right? It's not a different coolant, right, where then your plumbing becomes more complicated and you have to stuff more tubes, and maybe you have a couple more tubes in there for these little crossovers and stuff, right? But it's not a completely different system with completely different pumps and tanks, like you said. So that's what probably one of the, I guess you could say, genius of using this single thing. You're carrying it anyways. You're going to use it to get into space, deliver the payload. You're going to use it to cool the heat shield when you're coming back in. You're going to use it to land. too, and that one propellant, that hydrogen, does all of those things for you. That's cool.
That's right. Yeah, and I guess you hit on another thing that we didn't talk about yet, but it's a high-performing upper stage engine, and so in vacuum you want a very high expansion ratio in order to get the performance right. But it also has to operate at sea level on the ground at very low throttle, and so that factors into the equation also. How do you achieve that with a high-performing upper stage engine? You can't do it with RL10, you know. And so this set of discretized thrusters, with making some use of the aerospike effect, you know, kind of does that function for us. By the way, that's also why there's only 15 thrusters installed on Hopper instead of all 30. Basically running this thing with empty tanks and no payload. So we are mimicking the landing phase of flight when the whole thing's empty. There's not much mass in there. And so it's operating at very, very low throttle for this entire mission, the quote-unquote mission, the Hopper mission. And we don't, you know, part of the way we get the deep throttle is by turning off half the thrusters, and in Hopper's case, we just don't install them because why put them at risk?
Why put them there?
Yeah. Yep.
Keep them in the barn, keep them in the parts inventory, right? So
That's right.
Let's talk about that just a little bit, because these concepts are so cool. I want to make sure people understand. Andy mentioned expansion ratio, right? And so, you know, or if you've watched our channel enough, you know that there's probably different types of engines, and some engines are great for operating at sea level where there's air, there's atmospheric density around you, because that atmosphere sort of helps keep your exhaust. I talk about it, I've drawn it before, in a little pencil flame, right? And then every launch, I'm like, oh, you can see the expansion. As it gets into the thinner atmosphere, the plume expands out, it gets bigger, right? And there's less atmospheric density to sort of push that plume together. It's not a pencil anymore, it's a big plume, right? But when you get into space where there's no more atmosphere, you have to provide your own flow control, I guess. It's the engine bell. You see the engine bells on the engines that are optimized for space, and they're really huge engine bells, because when there's no atmosphere to help you out, you have to build a physical structure that keeps the exhaust going in a direction, so you can get more energy out of it. Okay? Well, these are tiny.
Yeah, you get more efficiency, you get more expansion, you get more thrust out of it, so it's a higher thrust, higher efficiency.
Yep.
So you want you want that to be as big as possible in space.
And then here on this design, these are all like small engine bells. We don't see, like, look at the CSM that went to the moon and that massive engine bell on the back of it, right? These are all tiny engine bells, but then how do you get to use this engine in both of these multiple regimes? That's the aerospike effect you were talking about, right?
That's right. Yep. Yeah. So you know, in the pictures that you saw, it's obviously operating in sea level. So the engine plumes, like you're saying, come together pretty quick. They're like very linear plumes.
Yep.
Excuse me, by design.
Plume.
And then when little pencils, and then when they go up into I guess the vacuum of space, those plumes expand and they actually merge together, and then they kind of create this continuous annulus around the heat shield, and then they trap some gas in the center core, right? So underneath the heat shield, they trap some gas, which is, you know, kind of the same thing as trapping some pressure. And so you get some pressure on the base heat shield there, and it's multiplied by an enormous area, huge area. Yeah, there you go. That's the picture.
Yep, that's it.
And so you get some bonus thrust just by the gas and the pressure that gets trapped in the center there. That is the aerospike effect, right? And make some amount of use for them. Yep.
Yeah, like you said at the beginning, you didn't set out to design an aerospike engine, but because of the way you're doing things, you get like a little bonus from the fact that this is probably too much of a stretch. I don't have a doctorate in rocket science, but the engine exhaust is almost acting as the engine bell to help you constrain that and get a little bit more ounce for your ounce, or whatever you want to call it, right?
Yeah, no, exactly. That's right.
All right. So it's amazing that you did that, and you've got that sort of design. So many different things going into the fact that this needs to go all the way into space and do its thing, and then come all the way back down again to get turned. You walk around it, kick the tires. I guess it doesn't have tires, but you know, put a payload in it and send it again. Let's talk about materials. So we talked to different rocket companies, and there's different camps of the materials that you actually build the main structure out of. Y'all have gone with I say more traditional. It's probably the wrong way to say it. Stainless steel, right?
Mm-hmm. Yeah, I think one of the things that the industry is learning as a whole is that there's a huge amount of value in being able to manufacture at high speed, especially during R&D. And so you want to be able to build fast. You want to be able to iterate fast. You want each increment to cost as little as possible. And so I think manufacturing kind of dictated this trade as much as anything. In this case, we chose stainless steel, as you said. This allows us to, first of all, there's it's commoditized alloy that we buy off the shelf from any number of suppliers in just like raw sheet metal form. So that's number one. Number two, it's pretty easy to work with. So that's good. We've come up with methods to build these structures that you're showing with really no fixed tooling and do so at a very high clip. There's talent base that's worked with it quite a bit. It's not super esoteric where you only pick from 3 people in the world to be able to work with this stuff.
Right.
And so a lot of things, you have to think about all those things. Now, when you look at it from a technical trade perspective, yeah, you might be able to use, high strength aluminum alloy to, on paper, get yourself a little bit more performance. But how are you going to get from nothing to market as fast as possible? It's a close enough trade where, to us, the manufacturing wins out every time. The other thing for the reusable second stage is that this thing is going to come back, and it's going to come back in a very hot environment. We have the heat shield on the forward side that's taking the brunt of the heat load, but the sides are also going to get hot. And so stainless has a much higher, heat tolerance or strength at temperature than aluminum would. So it helps us from that perspective as well. There's an anecdote that not many people know about, but shuttle came back, and here's another element of regenerative cooling over tiles. So shuttle came back, and you're coming back, the tiles are glowing white hot or red hot or whatever, and they're amazing insulators, which means the heat flux through them is very low. It takes time for heat to get from the hot side over into the structure. But at the end of the day, they are absorbing heat through that whole phase, right? So then it landed, and the heat is continuing to soak in the tiles. Tiles are still very, very hot. And so they actually had to plug in a separate water coolant circuit to shuttle when it landed in order to cool the structure so that the aluminum didn't overheat and lose its strength properties, right? No time for that. For us, we want to land and get moving, right? So I guess there's twofold. One, stainless steel is not susceptible to that as much. And two, this is the regenerative part. It comes back and it lands cold, right? It lands cold because it just had liquid hydrogen flow through the whole thing in order to perform that landing phase, right? So the whole thing is cold and approachable right from the second it touches down.
Who do I trust for business insurance?
For business insurance, join nearly 1 million customers who trust
On the Iceland swim, it's going to be quite similar to swimming around Great Britain, where you basically swim for 6 hours, sleep for 6 hours, swim for 6 hours, so you're swimming with the tide and then resting when it's against you. So you have almost this biphasic sleep, and at My Protein, we're so ahead of the curve. So it's so good. I'm constantly checking in with the guys at MPD, and they're just using me as like a little bit of a guinea pig, going, take this, do this, and disappear off out to sea, and that's exactly what I do.
Yeah, it's the different schools of thoughts there, right? Because we've heard of other rocket companies that are using carbon composites, right? And this very complicated thing, we're going to wind this up, we're going to build it, but that sort of makes a little bit more, I guess, slows you down in the manufacturing part a little bit. And with
I would say that the manufacturing is slow and expensive. They are right? There's two ways you can hack the rocket equation, which is, by the way, very, they talk about the tyranny of the rocket equation for a reason. We're on a planet where we can just barely get out of the gravity well with chemical propulsion. And so there's two ways to hack the rocket equation. One is with efficiency, specific impulse of your engines, performance of your engines. The number two part is with a mass fraction, so make the whole thing really light. And that's what the composites do, but it makes manufacturing very expensive and pretty slow. And then, there's some amount of question about how that survives reentry heat as well.
Gotcha. You said fixed tooling. So the structures that we were looking at were made mostly with no fixed tooling. Tell me if I'm wrong when I translate that a little bit. We've seen rocket factories, and it's like, here's this massive press that does this one thing. It's going to make this grid structure out of aluminum and make this tank. And it's this huge, massive thing. Is that what you're talking about when you mean no fixed tooling?
You just described fixed tooling. Typically millions of dollars in fixed tooling goes into this type of thing. And yeah, it was important for us to not do that because, first of all, we're a startup, we can't afford it. And second of all, we do want to maintain flexibility, right? Once you have all that fixed infrastructure, let's say you want to change the diameter of your tank by a little bit while you eat your hose, right? So then you start getting things locked in, and you really lose the flexibility to evolve, with yourself and with the market.
Gotcha. So you did not, you're still developing things, you're still testing hardware. You're not to the point where it's like, all right, now we are going to make 1,000 of these rockets in this design, and it's not going to change at all. You still are keeping the flexibility to change things a little bit, torque things. I don't know that you'd go through and make a wildly different tank right now. Maybe at some point you scale it up, right? But without those huge, massive machines, you sort of maintain that flexibility while you're still dialing things in. Is that the right way to say it?
Yeah, I think that's right. And I would also propose that I'm not sure on this, but I would venture a guess that there's been no rocket in history that's been made 1,000 times. And if you think about that, I think the Falcon second stage is probably going to be the first thing that gets there. But if you think about that from a production standpoint, that's one of the big things that makes rocketry so expensive is, we don't make these things a lot. Even a super high rate production for rockets is incredibly low rate production for just about anything else, right? And so if you put millions of dollars into fixed tooling in order to build this thing, maybe you're gonna make 100 or 200 or 300 of these, and it's just not a lot of units, right?
Especially if you're not throwing them away every time. If you are reusing them, rapidly or not, you have your fleet and you're operating more like the airline where nobody throws the 737 into the ocean every time you use it once, right? So you have to make less of them. You don't even need to make as many as you would have if everyone was once and done, right?
Right.
Good deal. Let's see here. We talked about the materials a little bit. We didn't talk too much about should I say payload fairing? Is it a cargo bay or is it a payload fairing? What do y'all call it on a reusable second stage?
Well, that's a great point. We call it a payload fairing, but maybe we should pivot.
Because normally, we joked a little bit about it, but rockets, in order to operate more efficiently, sometimes shed pieces. They throw things away, they don't keep carrying it, and SRBs come off because they're empty of fuel. And the payload fairing comes off because the atmosphere is thin enough that you don't have to protect the payload anymore. Rockets are constantly just throwing things off the side in a very controlled manner. For you, if you want to rapidly reuse this, you have to keep the vehicle sort of intact. And instead of a payload fairing that would deploy and tumble away, and we're like, you can see the fairings, they're falling away. They stay closed until you get to space, and then they open up and let a cargo out. Is that a huge design challenge? It's certainly not things that rockets normally do.
Yeah, I would say it's definitely a design challenge. Shuttle did the same thing with its bay doors, right? It's definitely a design challenge, there's no question. I think there's different types of missions that can be performed, and you can have these reusable fairings. You may choose to have deployable fairings also in certain cases. But one of the unique things that kind of falls out from using these reusable upper stages is that you're performing 3 modalities in every single flight. You're flying to space, and you have to do some amount of maneuvering in order to align with your landing site. So there's some movement in space that happens, and then there's the return aspect. And it turns out that those other two modalities, the through space and from space modalities, are valuable to certain people, right? For manufacturing in space, for various government partners and other things like that. And so there's a compelling case to be made where you may want to acquire something in space and bring it back down. You may want to just bring a hosted payload, have it perform a function, close the doors and bring that back down. There's a whole new set of missions, this whole new class of missions that are unlocked because you already do that on every flight, right?
Right.
And so, like I was saying, there may be cases where you want to use deployable fairings, but there may be cases where you don't, and you want to, have those closed up and bring something back and keep them protected.
You could just, I have to ask, just waggle your eyebrows. I assume you've done the math, but can the upper stage re-enter and land with or without the payload fairing on the top? Like if you had a deployable one where you did not bring it back down, is the vehicle still aerodynamically stable when it's coming down if it doesn't have the taper on the back?
From an aerodynamics perspective, it actually prefers that because when it's coming back down, you want it's all about center of pressure versus center of gravity. So you want center of gravity as far forward as possible, and you want center of pressure as far back as possible. But no fairings, you get rid of mass at a very high position in the vehicle stack. And you create all this drag in the back because it's this blunt, afterward-facing step kind of on the back, and so it helps both of those things. So aerodynamically, actually prefers no fairing up there.
Okay, so it could theoretically come down either way. I wonder how different the flight dynamics are. Like the software has to operate in this mode or that mode. Probably going to get there at some point, huh?
Well, I would say that's heavily analyzed on our end, at least.
Heavily analyzed on our end, nice. All right. And the other thing you said there was, you could go into space and retrieve something. We talk about space debris a lot of the times. Is it economically viable to retrieve space debris? Is it not? Well, if you have something that can go up there and grab a hold of something and then enclose it and bring it back, maybe it doesn't need to be enclosed, maybe it does, right? I don't know that we're there yet, but maybe one day we will need to bring some things back. Maybe more immediate is the ability to study things that have been operating in space for a long time. We don't have a lot of capacity to do that for discrete satellites and stuff. We have the ISS, the shuttle came back, right? But being able to go up there and retrieve a satellite that's been up there for X amount of time, is that something that you're looking at, like as a service?
Yeah. If it makes sense, if there are customers who want something. But I would say also, there's other, logical use cases. One of them is manufacturing in space, right? Anytime you manufacture something, you need a constant supply of raw materials to that manufacturing center, and you need a shipment of finished goods, right? And so you can imagine a scenario where you're on the way up delivering raw materials and on the way down bringing finished goods and byproducts, trash, whatever that may be. So that's one example. Another example would be space stations. One of the things that I'm super excited about Starship being successful is I think we finally will have viable commercial space stations. That's awesome. I would imagine that everybody listening wants that to happen. But once that very large infrastructure is put in place, you probably don't, as much as we all love astronaut ice stream and the novelty of it, probably don't want to be eating stuff like that every day. And so what you want is a constant shipment of food, or fresh food, produce, whatever that may be, supplies, etc. And then you need a return mission of trash. And so you imagine these different type of use cases or verticals, and there's a constant supply of goods to and from that location, and those are very easy to kind of comprehend. There's something else I was going to say about forgetting it.
Let's see. We're talking about going to and from space. That's something that we would, I think, all love to see. Rocket fans who like to see rocket launches and rocket landings. If there was more reason to be going to and from space, not just deploying satellites or just taking things up to the 1 or 2 or 3, the small number of space stations that we have, right? Imagine one day if there are 10 space stations or 20 space stations or orbital factories, like you said. You don't even maybe need people up there all the time, and you're just delivering raw materials and then picking up goods and bringing them back down and then landing them softly, not trying to splash them into the ocean and some of the things that we do. I, for one, hope to see that soon.
That's what it's all about. That's the future that we all want, right? And and you got to figure out how to do that in a way that's both scalable and sustainable. So this was the other thing that I was going to mention was the other thing that Starship does is puts millions of pounds into orbit, right? That's great, but then what happens to it? And I think that's a highly unknown question, right? You have millions of pounds of heavy metals or rare metals coming back, and if the way that we bring those things back is to burn them up in the atmosphere, at some point that's going to have an effect, right? And I think that's only just beginning to be studied now. But is it viable? Is that the right way? Just burn stuff up in the atmosphere and let it crash? I guess my hunch is probably not. I don't know, right? That's got to be studied, but I don't know.
Yeah.
And I think we'll probably want to collect things and bring it back. You asked the question, is there economic reason for us to collect trash and bring it down? And today, unequivocally, the answer is no. Who's paying for that? Nobody's paying for that. But at some point, I think there is regulation where you can't do what you want to do in space unless you clear your trash. And then it gets built into the cost structure of the economics of space activity. And then there is a paying customer, and then you have to do it. Right?
Yep. I mean, it really is the way that that space operates right now. We have things, they go into operational orbits, and then they either are done and they come back down and burn up, or they get graveyarded out, and it's basically just a junkyard, like a designated parking space for junk that we're done with. And we just leave it there. And we shouldn't probably operate that way forever. But there's no incentive otherwise. Like right now, there's nothing that says that a company needs to, well, you have to move your satellite to the trash orbit, to the graveyard orbit, right?
Well, the closest thing we have to it is you have to have a deorbit. From the time your satellite dies, it has to be out of orbit. And that just got switched from, I think it was 20 years to now 5 years. There's not really a great way to police it, though. Yeah, you have to have a plan. That's part of your FCC license. There's not a great way to police it, though, other than refusing future licenses, which may or may not happen.
Hasn't happened yet. There's been like the shot across the bow that happened a little while, like months ago, but there hasn't been a thing where that's really built in. So I don't want to overdo it too much, but it almost is. There's no incentive to do it. There's no, besides you have to do it.
Today, there's no incentive. That's all I'm trying to say. Today, there's no incentive to do it. And I think in the long term there will be, but it's going to take some time. It takes more study to understand, what are the actual impacts, and it's literal acts of Congress that we're asking for here, or we're talking about at least.
It's almost like safety training, right? Like there are regulations that say you need to be able to train the folks you work with to work safely, and so there's safety trainings. And then an entire industry has come up around training employees safely, and you could go hire a company that handles that for you, right? And we don't have that with orbital trash cleanup yet, but one day there might be a thing where that is a service that a satellite operator might go and buy from somebody. And so having the vehicle that can go to and from space and bring things back down and sort of operate in all those different modes makes it sort of the orbital tug and tow truck. I don't want to demean what a vehicle that is fully reusable could do, but it could do things like that, right?
Yeah, I think here's at the end of the day what you want. What we all want, what customers want, you want a couple things out of space mobility. The first thing is you want it to be low cost. The second thing is you want it to be much more on demand than what we have today, right? I mean, if you want to buy a standalone Falcon 9, it's like a 2-year lead time, which is great, right? There's lots of demand, but it's a long lead time. And if you think about if you're a startup and you're trying to figure out how you're getting to space, like do you want to use your very early seed dollars to reserve a spot in line for launch? No, you want to use it to prove your technology. So there's a balance there. But so you want low cost, you want on demand, and you want high reliability. And I think actually the beauty of full rapid reuse is it attacks all three of those three things at the fundamental level. So you get into this kind of virtuous cycle. The lower cost you have, the more demand you have, the more frequently you're flying. The more frequently you're flying, the better your reliability and the better your availability. And it just feeds on itself. That's beautiful. That's what you want, right? We're starting to see that is what Falcon has started to show us as an industry, but it is, I would comment that it is still like very, very much day one in our industry. And what rapid full reusability is a whole other order of magnitude in cost. And the same is true for availability, and then reliability follows as well.
Makes sense. There's a question that I've seen float through chat in a couple different formats here. But you mentioned the cadence, right? Like the more payloads you have to send, the higher your cadence is, the more experience you get, the better you get because you have an excuse to be flying. And it's great if those are paid for, right? You don't just fly to fly. If you have a paying customer or a service that you're providing by flying these payloads, it's good for you because you get the experience. And we see that with SpaceX and Starlink. There are so many launches that happened, and we're over here broadcasting launches, and we're like, oh, it's another Starlink at 3 a.m. Great. But because of that product that SpaceX has made, they've sort of created their own demand to launch their vehicles, and then they improve their vehicles, they improve their cadence, they get the experience. That is a brilliant way to do it, right? How is Stoke sort of approaching that? Do you have anything in the plans where we're going to launch this many vehicles this many times to help us get this experience? Like, you need payloads, you need excuses and funding to launch vehicles.
I think that the right way to answer that, I think, is it also feeds into the size of the vehicle. You want to have customers. You want to have enough customers who want to go to the same place at the same time always. And if you build a vehicle that's too big, then you can't fill the metaphorical seats of the vehicle, right? So if you think about, a great analogy is the airline industry, right? You have everything from Cessnas to A380s. And in the middle, there's a sweet spot where there's enough people to fill the seats who want to go to the same place at the same time, all the time, and those things are flying all the time. Those are the 737s and the A320s, right? A380 is already out of production because it's so big, the cost structure it's too expensive, and they can't fill the seats, so you can't fly enough, right? And so I guess that's. Go ahead. I was going to say that's what led us to this medium class of rocket, where I think there's enough other commercial customers who are going to we'll be able to fill our seats on every flight, and really we're actually the limiter, not the demand side. We'll fly as frequently as we possibly can, and there will always be demand, right? That's what you want. You want to be always pushing yourself to fly more frequently.
Gotcha. Because we're almost, I don't know, chicken, egg, cart, horse, demand before the supply, right? We're not in a situation right now where we have 15 commercial space stations and 20 orbital factories that are making crystals that are better to make in microgravity or low gravity, whatever you want to call it, right? We don't have that yet. And
no, but we do have probably 100 different satellite companies building small and medium-sized satellites, and they're all trying to get to orbit. And I think what a lot of those companies are finding are that their rideshare missions with Falcon 9 are great for proof of concept demo missions, but once you have to actually deploy a constellation where satellites need to be phased out in a way that works for you, those rideshare missions are no longer ideal, right? So now, what do? You're not going to buy a whole Falcon 9 for these small things. You need something else, right?
Let's make sure everybody understands that real quick, because I think a lot of people miss this. It's like, oh, I'm going to space, and I'm in space, I'm good, right? Well, you don't just want to get into space. That's like saying, I want to go to the US, I want to go to Germany, right? Okay, well, you're in Germany. Did you get to the right city where the tourist attraction you want to see is? No, you need to go to a specific place in Germany. You need to go to a specific place in the city. And so the rideshare is the plane that gets you to the proper country, right? But there's a lot of other places that you need to go. If you have something and you stack a bunch of stuff into a rideshare and you launch a bunch of them into the one orbit that you sort of end up in and get dropped off at, then the satellites have to make their way to their own orbits, right? And so then your satellite has to have more capability. You just use the term phasing. They have to be able to move into the useful spot that you need them. And the useful spot isn't always the spot that the rideshare drops them off, right?
Yeah, that's right.
Yeah. So when you have a smaller launcher, a medium launcher, then you can get put to the right building in the city, right? You get the exact destination that you're trying to go to, as opposed to, well, I got on the train and I ended up downtown and now I have to make my way to wherever it is that I'm going. That's where you get into the more specific orbit, not just ride along with everybody else.
everybody would rather fly direct than have layovers, and there's a very real time value of money associated with this. If you know, a lot of these orbit phasings take 6 months, 9 months to get from drop-off location to final location. You can see that in Starlinks, right? And for a company, if you look at it on economic terms, for a company, that
jumpers, t-shirts. Yeah, it's about £8 each. It's about £8 each for shirts alone. It's about £8 for 2 trousers. Only 2 trousers. You said you was gonna get extra. No. Yeah. No. That's cool. Mm. Yeah. Sure. But then you got it in cash. Because I haven't got internet on my phone at the minute. I haven't got my thing. Because I haven't got my internet on at the minute. Because I haven't got the internet on there at the minute. I can put back my internet on my phone yet. Yeah, cool. God knows how much it's going to cost. In like Tesco's, it's going to be like, in Tesco's, it's probably going to be either 25 or 25 or something for their shoe. Yeah. 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 It's up to you. Yeah, it's fine, but I haven't got internet on my phone to transfer because everything's in. Okay. That's not bad. Like, if that portfolio would have been a bit more helpful, you know what I'm saying? Because then I have a little bit of change left or whatever, but it's alright, it's 750, isn't it? Yeah, I'm blessed. Tired. Got a few left. Got a few left. Nothing I managed to do. Oh, gosh. It would be nice to have some just it there. Okay, and we need some bread as well. Breakfast. Okay.
Don't talk if I could have my tablet.
Yeah, of course you can. Hello, sweetheart. Okay. Hey, you baby boy. Yeah, right. You want something from the shop? What'd you like?
A magazine.
Oh.
I want a Spider-Man magazine. A Lego magazine like Spider-Man Lego. So you can order it.
I don't know, see.
my tablet.
Stay. Somebody look right there.
I'm looking at you in the camera.
Hey, little baby. Hey.
I don't really want my tablet to be dead because it's still not dead.
No, I don't tell you. Kadoosh, one more kadoosh. One more kadoosh.
I want to be in the blanket with you.
You want to be in my blanket? Oh. You're so cute. You're so cute, baby. Get a big boy.
I want to be. Let's see.
Okay, then let me have a quick fag first, yeah? Then, should we make a hot chocolate this morning? Hot chocolate?
If you make it now, I'm much more be more better.
Yeah?
Yeah.
Want a hot chocolate now?
Yeah.
Okay. I'm just not ready to get up yet. I'm just so not ready.
September.
1st of September. 1st of September, you go back to school? You'll be here too. Are you excited? Yeah? Yeah.
But I think Elijah can't show me like where is my classroom.
Well, we'll just see where everybody goes on Wednesday.
And then maybe all of my classmates. Wait, that's why I'm barely seeing me.
Because they didn't call the parents in to meet the teachers, did they?
Oh,
they
no,
didn't.
I see.
They didn't call us in to meet the teachers, did they?
Yeah, he isn't.
They didn't do that.
So maybe on parents' evening you see my teacher.
Oh, I'll see them before that, babe.
Mom, we're taking a video of our face.
Oh, you're taking videos of me, are you?
Yeah, but it's not on. I pressed this video, but it's not on. Oh, now it is on. Oh, finally, touch my tablet.
So, move it over a minute. Mm-hmm.
This mom already
Why is it so
has
loud?
5 sons, but her husband still wanted another boy. That's why she wanted to be the one to open the box, so that if Pink came out, it would be extra memorable for her. But then something completely unexpected happened. I'll show you. But first, if you think this dog is cute, make sure to like and subscribe. Look at this poor cat. He's all alone and just wants someone to care for her. So sad. If you have a heart, drop a heart in the comments and share it with everyone you know. Who knows? Maybe a million angels will bless your family for your kindness. When she
thought he was a girl. Bobby.
I'll go and get his like, uniform later. Trying to get out.
Look at this poor cat. He's all alone and just wants someone to care for her. So sad. If you have a heart, drop a heart in the comments and share this with everyone you know. Who knows? Maybe a million angels bless your family for your kindness. When she opened the box, she came out and she was so happy that she spun around in pure joy. This mom first show your age.
No.
Show how many bedrooms are in your house.
3.
Now show how many bathrooms are in your house. That's how many followers you need.
3.
First show.
Oh, Mr. Creature. The baby baby.
I'm just gonna tell you, it's my birthday! Ta-da! Just gonna tell you, it's my birthday! Ta-da! Just gonna tell you, it's my birthday! Ta-da!
Wait,
Just gonna
where's
tell you,
Mommy's
it's
hand?
my birthday!
Where's
I'm
Mommy?
here.
Ta-da!
Where's my hand, Mommy?
Just gonna tell you, it's my birthday! Ta-da! 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 Just gonna tell you, it's my birthday!
Well, what's the difference?
Oh guys, I'm about to be rare out here. Emily, make sure to like and subscribe. And if you're not new here, to do, show some lovely comments. Guys, in today's video, me and my mom are going to be swapping rooms. So we have a list of challenges, and at the end of the video, we have 5 minutes to find the special prize that each other hid in the room. So let's get started. But before we start doing the challenge, let's check out my mom's room. So we have this huge king-size bed, and why do they not have any pillows? Like, they have gray pillows, and then this, oh, this is soft. This is like not the same color, but it's really soft. I think it's for my mom's hair. She has truly hair. Now, let's go check out the nightstand. So let's do my dad's first. So what the heck? Why does he have this vanilla or lavender spray? Because I love guys. Just so now they use this stuff. Guys, his back has been hurting so bad. So I've been putting that on him. Hopefully he feels better soon. Well, now I'm in my mom's side, and what the heck is this? Wait, that's something. What? This is mine! Guys, my mom is stealing my stuff. Oh my god. Anyway, she has some press-on nails because, guys, her nails are so good. Like, she just bruh, why
babe.
I don't like a lot of things in my life, and you guys probably will see that I really have empty stuff in my room because I really don't want a lot of things in my room. So let's get started with the first challenge. Before we do that, let's do a little tour. She actually took this from us. I'm very proud of her. Her closet, never seen it this clean. That's really good. And then over here we got her school area, her desk area. She got her calendar in there, some stuff on the top. It's very cute, very cute. Very Sophia. Very Sophia. So let's get started with the morning routine. What I know Sophia does, because this girl, something about Sophia is that she is a routine girly. She does the same thing every day. So let's go. Let me see how I can recreate her. Now, before Sophia goes to bed the night before, she throws all of this things on the floor. I don't know why she has all of this things here because yeah, she throws them all over the instructions of the sleep. So why have all of this? Like I literally have my pillow. I have a hard pillow for my bed, soft pillow that I cuddle with, and I have a silk in my hair because I get all crazy. I just throw all this stuff on the floor because this is exactly how she does. After she spends like 10 minutes in bed rolling herself around, literally, like working out every morning, she goes to the bathroom and does her little skincare routine. So let's see what she has. It's been a while that I have checked her skincare routine. But this is Sophia's side of her bathroom. Right here she has a little necklace. Which one is this one? This is her cute one that has the S. She has a necklace, she has a little candle, her toothpaste, and her toothbrush all the way over here. Here, she'll basically just get ready for the day. She'll brush her teeth. Just gonna tell you.
Do you know Treno Struzzo Turbo 3000? Cara Struzzo Treno sui trillare. This is his story. Trenos was a naughty ostrich with super fast legs. His friends were scared of him because he was big and always causing trouble. Before we continue, don't forget to like and subscribe. Tell me in the comments what pet you have at home. Trenos loved to peck at other animals in the forest, and he often bothered a poor deer while it was sleeping. One day, he started chasing a rabbit and ran straight onto the train tracks. Suddenly, a train was coming right toward him. Crash! Trenos got hit, but something magical happened and boom! His body fused together with the train. From that day on, he was called Treno Struzzo Turbo 3000, the ostrich that became one with the Turbo 3000 train. But wait, Treno Struzzo Turbo 3000 even has a brain rot friend, a bird with a car's body. Who is it? Write your answer in the comments. Do you know Treno Struzzo Turbo 3000? Cara Struzzo 3000. Do you know? Penguinelli Cactusini. Here's his story. LaRue was a strong penguin with the heart of an adventurer. One morning, he left his colony and jumped onto a melting block of ice, drifting far across the ocean. Before we continue, don't forget to like and subscribe and comment. Do you love going on adventures too? After a long journey, LaRue finally reached a hot, dry desert. He walked through the sand until he found an old wooden hut. Inside the hut, he discovered a cowboy outfit, and of course he put it on right away. LaRue kept walking and walking, but soon he became very thirsty. There was no water anywhere. Desperate, he decided to eat a cactus, but something strange happened. The cactus released green liquid and boom! LaRue's body fused with the cactus. From that day on, he was never thirsty again, and everyone called him LaRue Le Penguinel Cactusini. But wait, in the desert, Penguinel Cactusini also had a brain rot friend, a camel with a refrigerator body. Who do you think it is? Write your answer in the comments. You know? Do you know Treno Struzzo Turbo 3000? What's a like and subscribe. And comment below. Do you have any debt to your friends? Kane was known for kicking street vendors' carts if they refused to pay him. One day, he approached an old man who was quietly painting a green chair. "You must pay your debt now, old man," Kane shouted. But the old man calmly replied, "I don't have the money yet, sir." Kane got even angry. He jumped on top of the green chair and stomped on it with all his strength. And then, boom, his body merged with the chair. It turned out the old man was actually a wizard in disguise. From that day on, Kane became a green cafe chair, and people started calling him Karkirker. But wait, Karkerkur has a challenge for you. Try to write Karkerkur Karkarkarkurkurkur with your eyes closed. Can you do it? Do you know? Do you know? Kurma dun 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 dun. Si bombasmi para manusia mokel. This is his story. Dudu was a rich and successful businessman. He owned the biggest date fruit store in the city. But Dudu was also a very arrogant boss who always did whatever he wanted. Before we continue, don't forget to like and subscribe. Only if you're not an arrogant person. One day, everything in the store was a mess because one of his workers made a mistake. At that moment, an old man who looked very hungry came and asked for some dates. But instead of helping, Dudu yelled at him and said, "I will never give dates to a beggar like you." The old man walked away and whispered, "May you face the result of your pride." Dudu got even angrier and started stomping on the dates that were scattered all over the floor. But suddenly, boom, his body fused with the dates. He cried and deeply regretted everything he had done. Since that day, people started calling him Kukurma Dun 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 Dun. But wait, Kukurma Dun 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 has a camel with a refrigerator body. Who is it? Write your answer in the comments. Do you know? Do you know? Nuclearo Dinosauro. La única. Do you know? Nuclearo Dinosauro. La única arma capaz de matarlo el bombardillo crocodillo. This is his story. One day, a military soldier was given a mission. Do you know, Chef? Do you know? Nuclearo Dinosauro. La única arma capaz de matarlo el bombardillo crocodillo. This is his story. One day, a military soldier was given a mission to investigate a cave near the military base. When the soldier entered the cave, he found a T-Rex fossil. After that, a military helicopter came and carried the T-Rex fossil to be researched. Before we continue, don't forget to like and subscribe and comment if you like dinosaurs. After arriving at the military laboratory, the fossil was studied with advanced machines.
Right,
It turned out that with the help of
nice
AI
comfortable
technology,
pillow.
the T-Rex fossil could be used as a military weapon. Since that moment, the military soldiers were ordered to start building a nuclear plane powered by the T-Rex. It turned out they did this to take revenge on Bombardiro Crocodiro, who once attacked their base. Finally, the nuclear plane powered by the T-Rex was finished and given the name Project Nuclearo Dinosauro. Nuclearo Dinosauro, controlled by the military commander, attacked Bombardiro Crocodiro's plane, and boom! Nuclearo Dinosauro succeeded in taking revenge for the military. But wait, Nuclearo Dinosauro has another enemy fighter plane. Who is it? Write your answer in the comments. Do you know? Nuclearo Dinosauro. La única arma capaz de... Do you know Chef Abracadabra? This is his story. George was a chef in a famous seafood restaurant, but he was very arrogant. Many people admired his cooking, but he always looked down on his assistant and said, "You will never match my skills." Before we continue, don't forget to like and subscribe. Aquí están mis robos.
Oh, can you make ketchup?
Do you know Greno Struzzo Turbo 3000, Karat Struzzo 3?
First, show your age.
9,
Then show how many bedrooms are in your house.
3. You have to go down.
Now show how many bathrooms are in your house.
3.
That's how many followers you
1.
have.
Oh.
First, show your age.
Sana buka.
Care about my well-being and myself. Yeah, so I'm always alone, babe.
Huh?
So I'm always alone. At home, by myself. Really, I would rather be alone by myself instead of being around people that don't care about my well-being. That's why I'm always alone. Yeah?
What did Daddy pick?
I'm not talking about Daddy, I'm talking about me, son.
What did Daddy pick? To...
Oh, I'm talking about me. Maybe I will rather be alone. Yeah, let me play that song for you. That's her. Oh my God, it's her. Yeah.
Let me see. What?
Yeah.
What?
First, show your age.
Trying to find something.
Then show how many bedrooms are in your house. Now show how many bathrooms are in your house.
Oh, this is it.
That's how many followers you need.
This is my favorite song.
All out on their newest update.
Look at the wall naturally and let people guess your zodiac.
Hate me, tell me how you hate me. Tell me how I'm trash and you can easily replace. I'm 23, and my folks are getting old. I know they don't have forever, and I'm scared to be alone. So I'm thankful for my sister, even though sometimes we fight. When high school wasn't easy, she's the reason I survived. I know she never leave me, and I hate to see her cry. So I wrote this verse to tell her that I'm always by her side. I wrote this verse to tell her that I'm always by her side. I wrote this verse to tell her that the world's not perfect, but it's not that bad. If we got each other, and it's all we have, I will be your brother, and I'll hold your hand. You should know I'll be there for you. I'm 23.
This is supposed to be for Brent and Lexi. I know them. They're YouTubers. So that was supposed to be for them.
What is that, babes?
I couldn't stop. Look at that. Ah!
Today we're going to be doing whoever stays under the water the longest wins. Alright, guys, man, I got all the kids lined up right now. We're going to see who can hold their breath under the water the longest. Who do you think they can? Alright, it's going to go crazy. Let's go. Ready? 3, 2, 1, go. How long do you think you can hold your breath underwater? You don't know? Let's see. Time to...
Let's charge my remote. Oh.
All you have to beat is 17
then we're going to be doing whoever stays under the water the longest wins. I just got, man, I got all the kids lined up right now.
Let's come up here.
Under the water the longest. Who you think they can?
Not really.
Let's go. Ready? 3, 2,
There it goes.